Far beyond the stars of the Milky Way, past the faint streams of the Virgo cluster, lies a solitary island of light known as the Sombrero Galaxy. It resides about 30 million light-years from Earth, on the boundary between the local group and the larger Virgo supercluster. In the darkness of space, it appears as a bright, flattened oval, crowned by a dark rim of dust, its halo stretching farther than human eyes can trace. The galaxy's light reaches Earth after travelling across cosmic voids, crossing filaments of intergalactic gas and the silent gravity of dark matter. Its shape is distinctive, recalling a wide-brimmed hat tilted against the blackness, a name chosen long before astronomers understood its true scale. From this distance, telescopes see the sombrero not as an isolated spiral, but as one participant in a greater cosmic structure. It belongs to a sparse group of galaxies loosely bound by gravity and separated by millions of light-years of near vacuum. Each system moves in slow orbits around a shared centre of mass, following paths determined by invisible dark matter. The background is filled with faint points, more distant galaxies of every size and colour, each another collection of billions of suns. Between them lies the cosmic web filaments of matter, stretching across hundreds of millions of light-years, shaped by ancient fluctuations from the earliest epochs after the Big Bang. The sombrero's environment is quiet. It is not caught in the turbulence of galaxy clusters where collisions and mergers are frequent. Its outer halo is undisturbed, and the surrounding space contains only a few smaller companions. Astronomers describe it as an early-type spiral or a lenticular hybrid, a system that bridges the forms between smooth elliptical galaxies and grand spirals like Andromeda. Its orientation to Earth is nearly edge-on, so the luminous bulge and dark equatorial ring stand out in sharp contrast. The thin plane of dust hides much of the disk from view, giving the illusion of a division between two hemispheres of light. At the scale of millions of light-years, the sombrero is a modest feature. It measures only about half the diameter of the Milky Way, though its central bulge is unusually bright and massive. The visible light from its stars combines into a soft yellowish hue, typical of populations rich in older suns. The galaxy's integrated brightness makes it one of the most luminous nearby objects outside the local group. Photons from its stars emitted long ago drift across space largely unimpeded, except for the rare scattering by intergalactic dust grains. The light is stretched by cosmic expansion, its wavelengths lengthened minutely over the journey, preserving a record of distance and time. One of the defining features of this galaxy is its large, smooth halo. Surrounding the main disk, this faint glow extends far beyond the visible edge, filled with ancient stars and dark matter that together contain most of the galaxy's mass. Its presence is inferred from the way the outer stars orbit faster than visible matter alone would allow. The same principle that revealed dark matter in other galaxies applies here. Rotation curves remain flat at great radii. The halo's invisible substance outweighs the luminous one binding the galaxy and maintaining its stability over billions of years. The sombrero's place within the cosmic lattice offers a view of contrast between density and emptiness. To one side lie the richer clusters of Virgo with thousands of galaxies packed into narrow space. To the other stretches a broad void, a region almost empty of stars and gas. The galaxy rests near this interface in a quiet corridor where external gravitational influences are minimal. Its evolution is therefore largely governed by its own internal processes: gradual star formation, slow accretion of matter, and the steady accumulation of dark mass. In cosmological maps, it appears as a small luminous bead along a filament that threads into the larger supercluster. Observations from space-based telescopes refine this portrait. Infrared detectors reveal the distribution of dust and old stars. Optical surveys record the intricate layering of the halo. X-ray observatories detect faint emission from hot gas, a sign of a gravitationally bound atmosphere extending far beyond the visible disk. Radio maps trace neutral hydrogen that moves gently in the outer reaches. These data converge to show a system in equilibrium not currently engaged in violent interactions. Its calm state allows astronomers to study structure and dynamics under nearly ideal conditions, without the distortions of tidal forces or ongoing mergers. The study of the Sombrero Galaxy also illuminates a broader theme in galactic science: the transition between different morphologies. Its characteristics challenge the simple classification schemes developed in the early 20th century. Though often labelled as a spiral, its bright spheroidal bulge and tightly wound dust ring resemble the features of lenticular systems. This dual nature suggests a gradual continuum rather than distinct categories. Such galaxies offer clues to how environment and history shape form, whether through ancient mergers, internal evolution, or loss of interstellar gas. A lesser-known detail lies in the extended stellar streams that faintly surround the halo. These diffuse arcs, only visible in deep imaging, may be remnants of smaller galaxies absorbed long ago. Their stars orbit the Sombrero, on elongated paths recording earlier interactions that no longer disturb the main structure. This evidence hints that even a quiet galaxy has a dynamic past. Yet many mysteries remain. The precise composition and temperature of its outer halo are uncertain, as are the details of its dark matter profile. The total mass, often estimated at several hundred billion times that of the Sun, depends on models that are still refined as better data arrive. The origin of its unusually large bulge compared to the disk also continues to puzzle researchers. Some suggest an early period of rapid star formation or a merger event in the distant past, but the lack of nearby debris clouds makes the sequence difficult to trace. Viewed on planetary scales, this galaxy's calm existence contrasts with the violent events that formed it. Over billions of years, its structure settled into balance between gravity and motion. Across its luminous span, tens of billions of stars orbit the center, with periods of hundreds of millions of years. Each star is itself a sun, with possible systems of planets and moons unknown to us. From the vantage point of the Milky Way, their combined light forms the delicate disk, and bright core captured in telescope images, a quiet spiral of innumerable suns adrift in a dark and patient universe. On the sky, the Sombrero Galaxy rests within the boundaries of Virgo, a quiet oval of light edged by a dark lane. But in space it occupies a more solitary address on the near approaches to the vast Virgo supercluster. Its distance of roughly 30 million light-years places it well in front of the crowded core of the Virgo cluster outside the region where galaxy encounters are frequent and tides are strong. This placement is a point of consensus. The Sombrero's projected against Virgo, but not a true cluster member. It moves within a relatively low-density corridor of the cosmic web, where gravity is gentle and the intergalactic medium is thin, and where a galaxy can preserve ordered structure over long spans of time. The broader environment is defined by filaments and sheets of matter that thread toward the Virgo cluster, with voids opening between them like black bays of deep space. Along one such filament, the Sombrero drifts with a small retinue of lesser systems, responding to the pull of larger assemblies without entering their turbulence. Within this neighbourhood, the background light of the universe is richer than what is seen from the local group because lines of sight pass near the crowded realm of Virgo. Across the galaxy's sky, the density of elliptical and spiral systems grows toward one hemisphere, while the opposite direction opens into sparser territory. The gravitational field echoes this asymmetry. The Virgo cluster acts as a distant attractor whose tides subtly shape motions over tens of millions of light-years. The Sombrero's orbit through this landscape is slow measured, in periods longer than the age of complex life on Earth. The conditions are favourable for the maintenance of a thin disk, and a luminous bulge-cold gas remains mostly bound. Stellar orbits remain nearly circular in the plane, and the outskirts are not stirred by repeated flybys. In this way, the setting works as a guarantor of calm, and the calm in turn preserves the record of the galaxy's internal history. The intergalactic medium in this sector is not empty, only diffuse. Hot, tenuous plasma lies between the galaxies, warmed by shocks and the general gravitational compression of the supercluster environment. It is too thin to strip gas from a galaxy like the Sombrero, yet present enough to host a faint glow at high energies when the right instruments look for it. The medium carries traces of metals forged by ancient stars drifting out of galaxies through winds and past outflows, and diluted to densities that are only inferred statistically. Over enormous timescales, this material may settle along the same filaments that guide galaxy motions, adding to the slow exchange of mass between systems and their surroundings. The Sombrero resides in the gentler margins of this circulation. A lesser-known detail of the Sombrero's environs is the presence of very faint extended structures that appear only in deep imaging around similar galaxies at comparable distances. In the Sombrero's case, observers report diffuse arcs and filaments around the outer halo when exposures are pushed to extreme depths, features that likely represent the tidal remains of small companions accreted in the remote past. These structures are not obvious in modest observations and do not reach the scale or brightness of the great streams seen around galaxies in denser environments. Their existence fits the picture of a system that has grown quietly, absorbing minor satellites without suffering the violent relaxation that rewrites a disk. The smoothness of the main halo supports this reading, as does the lack of nearby massive neighbours that could force strong distortions. The night sky, as seen from a hypothetical planet on the far edge of the Sombrero, would bear the signature of this environment. Toward the side facing Virgo, the arc of the sky would carry a field of distant galaxies more numerous and brighter than the opposite direction, their light faint but cumulative. The galaxy's own bulge would dominate the local firmament across a wide band, and the dust ring would cut a dark seam through the light. Far beyond the Virgo cluster would appear as a softly crowded region, where many small pale smudges gather. On planetary scales, the radiation background from the wider universe would be only slightly stronger than what is experienced in the Milky Way, a reminder that even in a supercluster, the gulf of space remains vast and the light of distant suns thinly spread. The Sombrero's group membership is uncertain in detail but broadly understood. Catalogues identify a sparse association around it, consisting of the Sombrero and several much smaller neighbours whose motions suggest a weakly bound configuration. The group lacks the dense intergalactic medium of a cluster, and does not display strong signs of recent mergers among its larger members. In such a setting, dynamical friction proceeds slowly, and the long-term fate of small companions is to spiral inward on timescales longer than the age of many stellar populations. This is an arrangement that encourages continuity. The outer disk shows little warping. The velocity field remains smooth, and star formation occurs at a modest pace in the lanes where cold gas is retained. Yet an unresolved mystery remains in the mismatch between environment and form. The Sombrero's bulge is exceptionally prominent compared with its disk, more characteristic of galaxies that have experienced significant early mergers or rapid dissipative collapse. If the local tides have been mild for much of cosmic time, how did such a luminous spheroid grow so large relative to the present disk? One possibility is that the decisive growth occurred very early, when the universe was more crowded, and gas accretion was faster, followed by a long interval of quiet that preserved the structure. Another is that minor mergers accumulated mass in the centre without destroying the disk. The evidence is compatible with both pathways and the environment offers few current clues to choose between them. The past event that set the balance may be too distant to be traced cleanly in the low surface brightness outskirts we can observe today. Kinematics give a further view of setting. The outer rotation curve stays level across great radii, a signature that the surrounding dark halo holds most of the mass, and that perturbations from neighbours are small. Where galaxies move through crowded regions, these curves can be scarred by interactions, or the gas disks can be truncated. None of that appears strongly here. Neutral hydrogen extends across the outer regions and follows ordered rotation. Ionized gas lines map a plane aligned with the dust ring and the stellar disk. The haloglobular clusters, which will be examined more closely in a later section, orbit in distributions that trace a deep, nearly spherical potential well. Everything points toward a system breathing in step with a quiet neighbourhood. From the vantage of large-scale structure, the Sombrero's corridor between cluster and void illustrates how the universe channels matter. Filaments feed clusters, and galaxies along those filaments feel the draw long before they arrive. The Sombrero's present calm does not mean isolation from this flow. Rather, it means coexistence with a current too broad and slow to ruffle a single disk. Over billions of years, the galaxy's path bends slightly toward Virgo, even as it preserves the layered architecture of halo, bulge, ring, and disk. On the grandest scale, this is what the environment provides: a long, steady frame within which a galaxy's internal processes write their slow record. In such a frame, the Sombrero can serve as a stable laboratory for understanding how gravity organizes stars and gas when external forces do not dominate the script. The halo of the Sombrero Galaxy spreads outward as a faint, almost imperceptible glow, a film of ancient starlight wrapped in a broader sphere of unseen mass. In telescopes, the disk and bulge claim attention, but careful imaging and measurements of motion reveal this wider, gentler structure extending far beyond the bright rim of dust. Astronomers use the word halo to mean two connected things at once: the visible halo of old, low-mass stars and the invisible halo of dark matter that frames and steadies the galaxy's entire architecture. The visible halo provides traces that show where gravity leads. The dark halo supplies most of the mass that binds the system together. Both are patient and both are older than many of the stars that shine in the ring and disk. A consensus view holds that the dark matter halo sets the stage for all later structure. The sign appears in the rotation curve, a plot of orbital speed against distance from the centre. In the Sombrero, the speeds do not fall away with radius, as they would if only visible matter were present. They hold nearly constant across the outer regions, implying a deep reservoir of mass whose light cannot be seen. This steady behaviour keeps stars in wide orbits and prevents the thin disk from flying apart. When the same analysis is applied to gas that drifts along the outskirts, the result matches the stars. The outer material moves in step with a gravitational field dominated by something other than starlight. This conclusion is not unique to this galaxy. It repeats across spirals and lenticular systems throughout the nearby universe, and the Sombrero fits that pattern cleanly. The visible halo adds texture to this framework. It is composed of very old stars, most of them born early in the galaxy's history, or accreted from smaller systems long ago. Their light is redder and softer than the young blue stars of spiral arms. At large distances from the centre, the surface brightness becomes so low that single stars can no longer be separated, yet their combined light still records their presence as a dim envelope. In deep exposures, subtle gradients appear, suggesting that the outer halo is not perfectly smooth. There are hints of faint seams and arcs, relics of tidal interactions that ended in absorption rather than disruption. These threads melt into the general glow at great radii, leaving only small departures from symmetry where a stream has not yet fully mixed with the background. A lesser-known detail comes from the way astronomers probe the sombrero's halo without resolving individual stars. Certain types of objects serve as beacons in the thin light, planetary nebulae. The glowing shells of dying suns can be detected as tiny greenish points in narrow bands, even when the surrounding stars are invisible. Their velocities measured through delicate spectra map the gravitational field far into the halo. Likewise, globular clusters orbit through the same space and act as test particles, though they will be considered in fuller detail later. These tracers outline a potential that remains close to spherical, even though the visible disk is flat. When their orbits are modelled, the mass implied at tens of thousands of light-years from the centre still rises with radius, another sign that the dark halo dominates the perimeter. Between the stars lies hot thin gas, whose presence is seen in high-energy wavelengths. It is not bright, but against a dark sky. The signal can be teased out as a diffuse glow. This gas belongs to the halo as well, filling it with temperatures of millions of degrees. The heat is a record of the depth of the gravitational well as gas falls inward. It is compressed and warmed to high energies, then supported by pressure against further collapse. The total content of this hot medium in the sombrero appears modest compared with massive clusters, yet real enough to confirm that the halo extends as a physical atmosphere beyond the luminous disk. It may carry heavy elements forged in previous generations of stars and expelled by winds and ancient supernovae, then diluted across large volumes where cooling proceeds slowly. The chemistry of halo stars tells a quiet story about formation. On average, the outer stars appear poorer in heavy elements than those of the bulge, a sign that they formed earlier or in smaller systems where enrichment was limited. Moving inward, the proportion of heavy elements rises, indicating longer or more intense cycles of star birth and death nearer the centre. This gradient hints that much of the visible halo was assembled from many contributors. Some stars formed inside the growing galaxy, others arrived by the slow dissolution of companions drawn in by gravity. The resulting mixture is not uniform, and in some directions one can read slight changes in colour with radius that correspond to changes in composition. Despite these inferences, an unresolved mystery remains in the precise structure of the dark matter halo. The inner profile may be steeper or shallower than simple models predict, and the transition between the luminous matter of the bulge and the invisible matter that dominates the outskirts is not settled with certainty. Different approaches to modelling the orbits of halo tracers produce subtly different shapes for the mass distribution. Some favour a more concentrated central mass surrounded by a gentle outer slope. Others allow for a broader, less peaked core. Better data reduce the range of possibilities, yet the family of acceptable solutions still leaves room for multiple histories of assembly. Whether early rapid collapse set the central density or whether repeated minor mergers massaged it into a different form is not a closed question. The halo's calm does not mean stasis. Even now, small objects pass through it, most of them too faint to be counted individually. Their orbits stretch into elongated paths, slowly processing under the combined pull of dark matter and the bright core. Over cosmic time, these bodies shed energy through weak interactions and deposit their stars into the outer regions. In this way, the halo continues to grow by small additions, thickening its light while preserving its overall symmetry. The process is slow enough that the disk and bulge feel little disturbance. Inside the dust ring, gas continues to follow ordered motion, while the halo absorbs the gentle rain of newcomers at the edge. Seen from a planetary scale, the halo's reach is difficult to picture. If the Milky Way's sun were placed at the sombrero's rim, the visible disk would span a broad band of sky, and the bright bulge would rise like a round pale cloud. Beyond that band, the halo would not appear as structure, but as a faint thickening of the night too uniform and weak to show edges to the eye. Yet it would shape everything. The speed of a hypothetical planet's star around the galaxy, the long period of its galactic year, and the slow drift of its trajectory through intergalactic space would all be set by the halo's mass. Even the density of high-energy particles arriving from outside the galaxy would be modulated by the extended magnetic and gaseous envelope that traces this mass. In that sense, the halo reaches down to the scale of atmospheres and oceans, influencing the environment in ways subtle and cumulative. Closer in, where the halo meets the luminous bulge, the balance between components becomes a matter of geometry. The spherical tendency of the halo blends into the roundness of the central light, while the thin plane of the disk cuts through both like the equator of a larger world. The dark matter does not follow the dust lanes or the stellar spiral. It simply surrounds them, indifferent to the cold-patterned structures drawn by gas. Under its steady pull, stars on low-inclination orbits maintain their thin alignment, while stars on high-inclination paths trace the more three-dimensional volume of the halo. Over time, the mixture of these orbits produces the smooth envelope seen at great radii. The extended halo therefore acts as the galaxy's memory in its frame. It stores the outcomes of early assembly records, the quiet addition of small companions, and steadies the rotation of the disk. It is at once too dim to command a casual glance and too massive to ignore. In the Sombrero, the combination of a bright central bulge, a sharply defined dust ring, and this wide, nearly spherical envelope offers a clean view of how a galaxy can be both layered and unified. The outer light whispers of ancient stars. The unseen mass holds them in place. The whole system turns slowly within this invisible boundary, a silent sphere that contains a spiral shape and the long record of billions of suns. Around the Sombrero Galaxy, a swarm of ancient star clusters orbits, in broad ellipses, a population so rich that it reshapes the impression of the halo itself. These globular clusters are dense, nearly spherical families of stars bound by their own gravity, each one a compact system that formed early in the galaxy's history. In the Sombrero, their number reaches into the realm of a few thousand, far more than the tally around the Milky Way, and large enough to act as precise tracers of mass and structure. The consensus view is that the Sombrero is unusually wealthy in such clusters. For a galaxy of its size, a feature that aligns with its bright central bulge and the quiet dignity of its outskirts. The clusters arrange themselves into a broad three-dimensional distribution that extends far beyond the luminous disk and dust ring, and their motions outline a gravitational field that remains deep and nearly spherical at large radii. Observers map this swarm through careful imaging and spectroscopy. In wide fields, the clusters appear as tiny, slightly blurred points, fainter than stars in the foreground, and redder or bluer in characteristic ways. Space telescopes resolve their compact shapes and separate them from background galaxies, while large ground instruments measure their velocities from the small shifts in spectral lines. These measurements show that the clusters move in an extended halo that is only loosely aligned with the plane of the disk. The orbits are not purely circular. Many are inclined and elongated, a sign that the cluster system, like the dark matter halo that hosts it, is not governed by the thin geometry of the dust ring. The distribution of speeds and directions points to a mass that swells gently with radius, confirming that the unseen component outweighs the starlight at the perimeter. The colours of the clusters reveal a second layer of structure. When their light is measured through filters and plotted, a bimodal pattern appears. One group tends toward bluer hues associated with lower heavy element content, while another group is redder and more enriched. This division echoes a common theme in large galaxies. The blue metal pore clusters spread into a wider, more extended halo, often reaching to great distances. The red metal-rich clusters concentrate more toward the luminous bulge and inner regions. In the Sombrero, this pattern is pronounced, and it suggests two broad pathways of formation. The metal pore clusters likely originated in early relatively small fragments of the proto-galaxy, or in satellites that were later absorbed. The metal-rich clusters point to a formation epoch when gas had already been enriched by previous generations of stars, perhaps during periods of intense central star formation that helped build the bulge. The age estimates place both groups among the oldest stellar populations, with formation times clustered in the young universe, when the raw material was abundant and the overall density was higher. A lesser-known detail of the Sombrero's cluster system lies in its unusually bright upper end. Among the many compact clusters are objects that rival the most massive globulars known nearby, with luminosities and sizes that border on the territory of stripped galactic nuclei. Some of these bright clusters show hints of internal complexity, such as extended light profiles or subtle colour gradients, features that may indicate a more complicated history than a simple single burst of star formation. They could be the surviving hearts of small galaxies that lost their outer stars to the tidal field of the Sombrero long ago. In that reading, the cluster system remembers not only conditions inside the main galaxy, but also the quiet absorption of companions across cosmic time. These exceptional clusters are few, yet they provide a bridge between ordinary globulars and the smallest dwarf galaxies, underscoring the continuity of structures that gravity can shape. The clusters do more than trace mass and formation history. They also calibrate the distance to the galaxy. The brightness distribution of globular clusters follows a characteristic pattern whose peak can be used as a standard candle when enough clusters are observed. In the Sombrero, this method supports a distance of tens of millions of light-years, in agreement with other techniques and reinforcing the placement of the galaxy in front of the Virgo cluster. The same approach helps separate the cluster system from unrelated background galaxies, thereby refining the census and improving measurements of spatial distribution. The result is a clean view of how the clusters thin with radius, how they align with the bulge, and how their densities change from one side of the galaxy to the other. At high energies, the cluster system adds a further compact signal. Some clusters host low-mass X-ray binaries, small stellar remnants in close orbits that accrete matter and flash in hard light. These binaries are more common in dense stellar environments, and their presence in the Sombrero's clusters follows the same pattern seen in other galaxies. The correlation between cluster mass central density and the likelihood of hosting such a source provides an indirect probe of internal structure at scales too small to resolve directly at this distance. It also connects the globular population to the life cycles of stars, showing how ancient systems continue to produce energetic phenomena even after their major episodes of star formation have ended. Despite these insights, an unresolved mystery stands at the core of interpretation. Why does the Sombrero possess such a high specific frequency of clusters relative to its stellar mass? And what sequence of events set the balance between blue and red subpopulations? Models can reproduce large cluster systems through different routes. One path invokes an early rapid collapse that formed the bulge, and a rich cohort of metal pore clusters before feedback quenched star formation in the outskirts. Another relies on the prolonged quiet accretion of many small satellites, each contributing a handful of clusters that built up the blue halo over time, while the red clusters formed during centrally concentrated starbursts. Both pictures can be tuned to match the present numbers and distributions within uncertainties. The lack of strong tidal distortions in the current disk favours the idea that any significant mergers happened very early or were minor, but the data cannot rule out every variant. The truth may be a combination, with an initial burst setting the stage and a long reign of small companions filling the halo. Chemistry and dynamics offer partial constraints. The The metal-poor clusters show a mild trend in which the more massive among them are slightly richer in heavy elements than the lighter ones, a mass-metallicity relation sometimes called a blue tilt. This pattern hints that deeper gravitational wells inside large clusters can retain stellar ejecta and self-enrich, or that the progenitor fragments that birthed the largest clusters were themselves more enriched. Meanwhile, the red clusters, being more centrally concentrated, carry kinematic signatures closer to that of the bulge. Their orbits are somewhat rounder on average, and their velocity dispersions mirror the depth of the central potential. Together, these clues point to a formation history that scaled with environment. The inner regions grew richer earlier, and forged red clusters amid intense star formation, while the outskirts remained a domain of blue clusters arriving from smaller contexts. On a planetary scale, the presence of such a populous cluster system would be visible in quiet ways to any observer inside the galaxy's halo. On cloudless, moonless nights in a world far from the bright bulge, the sky would host many compact hazy stars that do not twinkle like single suns. Each globular would appear as a tiny concentrated glow with a denser heart and a soft edge rising and setting with the slow rotation of the planet's sky. Through simple instruments they would resolve into grainy spheres with countless faint points woven into a round tapestry. Over seasons, some clusters would slide gently against the background of more distant galaxies, their proper motions too small to notice without patient records, but their positions predictable once charted. The radiation from these clusters would be gentle, and their gravitational influence on a single world would be negligible, yet their presence would lend the night an extra layer of depth, a reminder that the galaxy's halo is not emptiness, but an archive of dense star cities drifting in orderly paths. Closer to the luminous disk, the cluster density would rise slightly on the sky, especially where lines of sight cut through the richer, redder subpopulation that crowds the bulge. The dust ring would still draw a dark seam through the light of the inner galaxy, and the clusters would frame it like scattered embers, though most would lie above and below the plane. Their orbits would carry them through pericenters nearer the centre, and epicenters far outside the visible edge, stitching the halo with long, stable loops that take hundreds of millions of years to complete. In aggregate, their gravity is small compared with the dark halo's pull, but their number and distribution provide one of the most detailed maps of that pull that astronomers can draw at this distance. In the Sombrero Galaxy, the globular cluster swarm therefore plays three roles at once. It is a fossil record of early conditions that preserves ages and compositions from an era when the universe was denser and more active. It is a dynamical tracer that outlines the mass of the halo and the shape of the potential well over vast scales. It is a continuing quiet engine of compact phenomena, where dense stellar environments nurture interactions that light up at high energies. The richness of the swarm aligns with the brightness of the bulge, and the calm of the environment forming a coherent picture of a system that assembled early strength and then evolved in relative peace. The details of that assembly still leave room for multiple histories, but the clusters themselves hold steady circling in patient bands that lace the galaxy's edge and keep time with a rhythm measured in orbits longer than continents have existed on Earth. A dark, continuous ring of dust encircles the bright central light of the Sombrero Galaxy and defines its profile on the sky. Because the system is viewed nearly edge on the ring, appears as a narrow, opaque lane crossing the bulge, but in 3 dimensions it is a broad annulus of gas and microscopic grains wrapped around the inner galaxy. This structure belongs to the outer disk, yet stands apart from its smoother stellar background by virtue of composition and opacity. It is the most recognizable feature of the Sombrero, and a consensus anchor for its classification a galaxy, with the luminous spheroid set within a cold dusty ring that holds much of the interstellar material available for star formation. The ring's geometry, composition and gentle activity together explain why the galaxy looks the way it does and why its light is divided into bright and dark. The dust that forms the ring is a mixture of silicate particles, carbon-rich grains, and complex molecules that absorb and scatter blue and visible light while re-emitting absorbed energy in the infrared. In optical wavelengths, the effect is strong extinction, which creates the sharp seam across the bulge that gives the galaxy its outline. At longer wavelengths, the same ring glows, revealing contours that are invisible in the optical band. Infrared maps show that the peak of emission lies not at the very centre, but along the annulus, confirming that the coldest, densest interstellar material concentrates there. Radio observations of neutral hydrogen and molecular lines trace the same shape, with the densest molecular gas aligned with the dark lane. Together, these data define a ring that is wide in radius, relatively thin in vertical extent, and continuous around the galaxy, with only mild asymmetries caused by inclination and local variations in density. A lesser-known detail emerges when the ring is measured carefully across wavelengths. Its mid-infrared brightness can rival or exceed the combined starlight of the disk at those frequencies, even though it looks dark in visible light. This inversion underscores the dual role of dust as both veil and lamp. Where starlight passes through the annulus, it is dimmed and reddened, making the bulge appear split. Where energy absorbed by grains escapes in the infrared, the ring becomes the galaxy's most luminous band in that regime. The contrast allows astronomers to separate the distributions of old stars and cold material, cleanly making the Sombrero a case where both components are mapped with unusual clarity. The same maps show faint spokes and knots along the ring signatures of density waves or local turbulence that gather gas into clumps where stars may form at a modest rate. The geometry of the ring carries information about dynamics. Its near-circular shape and narrow vertical thickness imply a population of gas clouds on low-inclination, nearly circular orbits. The smoothness suggests that non-circular motions are weak, and that strong external perturbations are absent. Small offsets in the apparent edge and slight brightness gradients from one side of the bulge to the other arise because the ring is tipped with respect to Earth's line of sight by only a few degrees, so one half lies slightly nearer, and its dust lane eclipses more of the bulge's starlight. Kinematic measurements show that the gas rotates swiftly and coherently, matching the ordered field traced by stars in the outer disk and by planetary nebula in the halo's inner edge. In simple terms, the ring is the densest seam in a rotating sheet of material that wraps the bulge. Star formation in the ring proceeds calmly, compared with grand design spirals where bright blue arms mark high rates of new star birth. The Sombrero's annulus hosts a quieter cycle. Ultraviolet and hydrogen recombination lines reveal stars in patches, but the overall rate remains low for a galaxy with such a large reservoir of molecular gas. The dust grains masses help regulate this balance, cooling clouds by radiation, while also shielding interiors from harsh light. The result is a set of dense clumps embedded in a cooler medium with local bursts of star formation that do not dominate the integrated light. In this state, the ring preserves its mass over long intervals, replenished slowly by infall from the outer disk and shaped by waves driven from the inner regions. The composition of the ring evolves under gentle feedback. Dying stars enrich the surrounding gas with heavier elements and dust, while radiation from young hot stars modifies the smallest grains and molecules, including polycyclic aromatic hydrocarbons that glow at characteristic wavelengths in the mid-infrared. Over time, these processes maintain a mixed inventory of grain sizes from fine smoke-like particles to larger pebbles on submicron scales. Observations show that the Sombrero's ring contains enough of these materials to account for its strong infrared output, yet not so much that the disk becomes opaque off the midplane. This balance produces the striking silhouette without smothering the light of the outer disk entirely. An unresolved mystery concerns origin and permanence. Does the ring owe its existence to slow internal evolution under the influence of resonances set by the galaxy's mass distribution, or did an external event seed or reshape it in the past? In many galaxies, rings form near dynamical resonances created by bars or oval distortions where gas accumulates as it loses angular momentum and settles. The sombrero's very bright bulge and the hints of an inner oval or weak bar suggest that such resonances may operate here, funneling material into the annulus at preferred radius. Yet it remains possible that the ring also remembers an earlier accretion of gas from outside, perhaps the remains of a small companion whose material settled into the plane. The present calm does not select one history uniquely. The lack of strong warps or obvious tidal tails points to a quiet recent past, but it does not erase older events that have already mixed. The ring also records the gravitational boundary between components. Outside the annulus, the potential is dominated by the dark matter halo and the combined mass of the stellar disk. Inside, the luminous bulge rises rapidly in importance. The ring sits near the radius where these influences are comparable, and in that zone small changes in the mass distribution can create stable orbits for gas that collect into persistent narrow structures. This placement may explain why the ring is long-lived. It lies where the inward pull of the bulge and the outward centrifugal tendency of rotating gas balance in a way that damps large excursions. Measurements of rotation and line widths confirm that velocity dispersions in the ring remain modest, consistent with a thin layer that resists vertical puffing. At planetary scales, the consequences of living within such an annulus are concrete. On a world orbiting a star embedded in the mid-plane, the sky would show a broad dark band against the glow of the inner galaxy, not because light is absent, but because dust sifts and dims it. The bulge would appear as a luminous dome split by the lane, with the nearer half slightly darker where the line of sight passes through more material. Nights would carry a mild, far infrared glow from heated grains too soft for eyes but present to instruments. The interstellar medium would be cooler and denser than in the bulge, with higher extinction between nearby stars and subtle reddening of starlight. Navigation by distant galaxies would be uneven toward the ring's tangent points. The background would be masked, while above and below the plane the view would open into deep space. The coupling between gas dust and starlight in the ring sets a local climate for star formation. Regions where spiral density waves compress the medium become nursery zones shielded by dust shells that keep ultraviolet radiation from evaporating nascent clouds too quickly. Elsewhere, turbulence and shear stretch clouds into filaments that resist collapse. Over millions of years, these processes convert a fraction of the gas into stars while leaving much of it in a diffuse rotating reserve. Because the sombrero avoids strong external disturbances, the ring's internal cycle can operate without large shocks or ram pressure to strip it. The result is a steady low-intensity churn that slowly refreshes the stellar population of the outer disk. Measured against the galaxy's total mass, the ring contains a small but crucial share of baryons. It stores the material that most directly shapes the visible profile and the color of the light, even though the dark matter halo supplies most of the gravity. It also acts as a transport layer. Gas moves through it inward and outward, over long times responding to torques from the inner potential and to weak patterns in the disk. In this sense, the ring is not merely a static rim, but a conveyor that moves mass and angular momentum across the boundary between outer disk and inner regions. Evidence for this motion appears in subtle gradients of metallicity and in the alignment of dust lanes that curve gently as they approach the bulge. The sombrero's dust ring therefore stands as a practical physical structure rather than a mere silhouette. It is a cold rotating annulus, where grains and gas collect, where starlight is filtered and re-emitted where new stars form at a measured pace, and where the forces of the galaxy balance to allow a thin layer to persist. It is stable enough to confer identity and dynamic enough to evolve carrying signs of both long-term equilibrium and slow transport. Its prominence in images is a reminder that visible light records only part of a galaxy's story, and that the darkest features may be the densest places where matter gathers. As the path moves inward, the ring marks the threshold between the broad, faint outer disk and the brighter inner architecture that the bulge dominates. Beyond the dark ring, the Sombrero Galaxy spreads into an outer stellar disk, a wide, faint sheet of older light that carries the ordered rotation of the system to large radii. From Earth, the nearly edge-on view compresses this region into a slim band, yet careful profiles measured along the major axis reveal its gradual decline in brightness and its quiet continuity. The disk does not shout with clumpy star-forming knots as in grand spirals. Instead, it presents a smooth field of yellow to red starlight, whose combined glow thins gently outward. The consensus picture is that this outer disk is dynamically cold in the plane vertically thin, compared with its radius, and supported against collapse by the balance between rotation and the small random motions of its stars. It is here that the galaxy's rotation curve remains close to level, indicating the sustained reach of the dark halo, while the visible contribution drops away with distance from the centre. In this domain, geometry rules the appearance. The outer disk is inclined only slightly from perfect edge on, so lines of sight pass through long paths of starlight and dust before emerging into the halo. The result is a thin, luminous bar on the sky, punctuated by the dust-lane silhouette near the inner radii, but increasingly free of extinction farther out where the column of material diminishes. When the light is decomposed into bulge ring and disk using standard models, the outer disk contributes a modest yet significant fraction of the total luminosity, enough to define the galaxy's outline, while leaving the central bulge to dominate the eye. The vertical profile in this region is well described by a thin component with a small scale height and a fainter, thicker envelope that contributes weak wings to the light above and below the plane. The thin layer contains most of the young to intermediate age stars such as they are, and the thick layer carries older, kinematically warmer populations. A consensus detail emerges in the radial surface brightness curve. Rather than a single unbroken exponential decline, many edge-on disks show subtle changes of slope, and the Sombrero belongs to this family. At a certain radius beyond the bright ring, the decline appears to relax slightly, as if the disk transitions into a more extended outer component with a shallower fall-off. This anti-truncation or upbending profile remains a gentle effect here, not a sharp break, and it may reflect the contribution of the thick disk or faint stellar structures stirred by past minor accretion. Because the galaxy is so bulge-dominated, the outer disk's upturn is not dramatic in integrated light, yet careful photometry traces it as a real feature. It speaks to a wide sheet of stars that continues comfortably beyond the radius where dust and gas are most concentrated. The colours of the outer disk tell a consistent story. Moving outward from the ring, the integrated light grows slightly bluer before settling into a steady old hue. The initial shift reflects the reduced extinction and the modest presence of intermediate age stars where gas is still available, while the outer steadiness indicates a population dominated by long-lived, low-mass suns formed in earlier epochs. The gradient in heavy element content across the disk remains mild at these distances. Enrichment is lower than in the inner regions, but not as metal-poor as the farthest halo. This composition suggests that much of the outer disk grew by inside-out formation, with gas gradually settling and forming stars over long periods, while minor additions from small satellites salted the outskirts with stars that shared similar ages but slightly different chemistries. The absence of strong blue patches at great radius fits the low present rate of star birth and the calm environment A lesser-known detail lies in the vertical flaring of the outer disk. Many spirals display a slow outward increase in the thickness of the stellar layer, a natural outcome of weaker vertical gravity where the mass density drops. In the Sombrero edge-on profiles indicate just such a gentle flare, with the thin component broadening subtly beyond the bright ring. The effect is small and smooth, visible only when data are stacked along wide swathes of the major axis and modelled with care. Its presence signals that the stars maintain slightly larger vertical motions at the edge, either inherited from their birth conditions or acquired through millions of small gravitational nudges from spiral waves, molecular clouds, and the quiet pull of unseen substructure in the halo. The flare blends into the faint, thick components so that no discrete seam marks the transition, only a slow easing of the disk into the surrounding envelope of light. Kinematics confirm the disk's ordered state. Spectra taken along the line of nodes show that rotational speeds remain nearly constant with radius in the outer regions, while dispersions perpendicular to the plane stay low. The ratio of rotation to random motion is large enough that the disk avoids strong buckling instabilities, and the measured asymmetries between the approaching and receding sides are small, consistent with a symmetric mass distribution and the absence of recent tidal disturbance. Neutral hydrogen mapping, though faint at the periphery, follows the same rotation, providing an independent check that gas and stars share the overall angular momentum field, where ionized gas emission lines can be measured. They trace the same sense of motion but fade quickly outside the ring, underscoring that the outer disk is primarily a stellar structure with only a thin veil of gas. An unresolved mystery touches the origin of the outermost stars. Are they the relics of a once more gas-rich disk that quietly exhausted its reservoir and aged in place? Or are they the accumulated products of a slow drizzle of stars from small companions that settled into near-planar orbits? The smoothness of the light and the continuity of rotation argue for long residence in the disk, rather than a dominant contribution from randomly oriented accretions. Yet the mild anti-truncation and the presence of very faint loops in deep exposures suggest that minor mergers did occur and left delicate imprints. It is likely that both channels contributed with in situ formation, prevailing over most radii, and occasional additions from satellites thickening the periphery and lending it a subtly different texture. Distinguishing the balance remains difficult at the Sombrero's distance, where individual stars cannot be resolved to read their ages directly. The energy budget of the outer disk is modest. Starlight provides most of the luminosity, with dust emission dropping as the column density falls. The radiation field is weaker than in the inner regions, allowing small grains to survive longer and molecular clouds, where present, to remain cold. Cosmic rays and magnetic fields thread the disk, but their influence on large-scale dynamics is slight compared with gravity and rotation. Over tens of millions of years, the slow diffusion of angular momentum spreads stellar orbits slightly, while the scarce gas drifts under gentle torques toward resonant radii nearer the ring. Stellar mass loss replenishes a thin component of warm gas, which cools and either joins the few remaining clouds or escapes into the diffuse medium where it is carried by the disk's rotation. On planetary scales, a world embedded in the outer disk would experience a sky with a low, even glow. The bulge would still dominate one direction, but its light would be fainter and more sharply bisected by the lane near the plane. Above and below the thin midline, the night would open into the dark of the halo, and beyond that into a spray of distant galaxies. The interstellar extinction between neighbouring stars would be reduced compared with the ring, making the local stellar neighbourhood appear cleaner, while the far infrared background would be correspondingly lower. Seasonal variations in the galaxy's appearance would be set by the planet's axial tilt and orbit, rather than by nearby star-forming complexes, because such complexes are rare here. The night would feel old and steady, lit by countless long-lived stars that change only over spans too long to imagine. Dynamically, life in the outer disk proceeds under gentle tides. The vertical gravitational pull weakens compared with the inner regions, so stellar systems oscillate more slowly above and below the midplane. The period of a galactic year at these radii lengthens to hundreds of millions of years, and the shear between adjacent circular paths softens. These conditions reduce the frequency of close passages between stars and help preserve wide binary systems that might be disrupted in denser environments. Planetary systems feel fewer external jolts. Comet reservoirs are perturbed mainly by internal dynamics, rather than by passing stars. In this sense, the outer disk is a quiet suburb of the galaxy, set far from the crowded avenues near the centre. The outer disk's relationship to the dark matter halo frames its long-term stability. The near constancy of rotation speed means that the halo provides most of the radial support here, while the disk's own self-gravity shapes local structure, including any faint spiral patterns too subtle to see in an edge on view. If weak arms exist, they act more as kinematic ripples than as engines of major star formation nudging orbits without gathering large gas masses. The absence of prominent warps in the light implies that the angular momentum vectors of the disk and halo are well aligned, or that any misalignment is small. The gentle vertical flare can then be understood as the natural outcome of low density, rather than as a signature of torque from an inclined halo. In integrated view, the outer stellar disk of the Sombrero is a record of endurance. It holds the remnants of earlier, more active epochs, but it does not produce strong new features of its own. Its stars orbit in quiet order, their combined light tapering to the edge where the disk meets the broader glow of the halo. The profile shows the faintest hint of extension. The colours settle into an old tone, the thickness eases outward, and the kinematics hold steady. These are the marks of a disk that has avoided recent violence and has aged within a stable gravitational frame. As the path of description proceeds inward, this outer sheet serves as the calm foundation upon which the brighter inner architecture rests, a wide, thin memory of slow rotation and patient light. Between the stars of the Sombrero Galaxy lies a layered interstellar medium, a mixture of gas dust, radiation, magnetic fields, and high-energy particles that fills the space from the midplane of the disk to the soft limits of the halo. It is not a uniform substance, but a set of coexisting phases that share pressure and exchange material. Cold molecular clouds dense enough for molecules to survive. Cold neutral hydrogen that blankets the ring and outer disk. Warmer atomic gas that carries much of the mass where the density drops. Diffuse ionized gas that glows faintly in recombination lines. And hot thin plasma that spills upward from the disk and blends into the halo's X-ray atmosphere. Together, these phases organize around the galaxy's rotation and the quiet gravitational field, forming an ordered, low-turbulence environment that reflects the Sombrero's modest rate of star formation and its unusually bright bulge. A consensus portrait begins with the coldest reservoirs. In the dark annulus, the density of gas and dust peaks, and there the conditions allow hydrogen to assemble into molecules that are traced by emission from associated species in the radio band. These molecular clumps are not as numerous or as massive as in grand design spirals, where bright arms mark intense star birth. Yet they are present as the seeds and stores of future stars. Their temperatures remain low because dust grains radiate away heat efficiently in the infrared, and because the overall radiation field is softened by distance from the central light. Shielded interiors protect fragile molecules and allow solid particles to grow mantles of ices. The clouds drift on nearly circular orbits, shear gently in the galactic tide, and collide only rarely compared with the busy inner disks of more active galaxies. Surrounding and threading through these cold condensations is the cold neutral medium composed largely of atomic hydrogen at temperatures of tens to a few hundreds of degrees Celsius above absolute zero on astronomical scales. Radio maps of the line emitted by this hydrogen trace a ring-like distribution aligned with the dust lane and continue outward into the faint stellar disk. The signal shows coherent rotation and a vertical thickness that increases slowly with radius. Where the gas surface density slips below the threshold for molecule formation, the cold neutral medium becomes the dominant reservoir by mass supplying material that may later cool compress and cross the boundary into the molecular state when local conditions permit. Warmed by starlight and by gentle shocks, is the warm neutral medium a more diffuse phase that shares volume with the cold gas but occupies a larger fraction of space? It carries a significant share of the interstellar pressure and acts as the connective tissue between dense clouds. Beyond it lies the warm ionized medium identified by its faint optical emission lines that appear when electrons recombine with protons and with more complex ions of heavier elements. In the Sombrero, this diffuse ionized layer is present but restrained consistent with a galaxy whose star formation rate is low and whose population of hot short-lived stars is small. The ionized layer extends above and below the plane by a modest distance, forming a pale envelope that responds to the slow leak of energetic photons from the midplane and to the small number of supernova remnants that ventilate the disk. Dust grains pervade all of these phases and shape the appearance of the galaxy. In the optical band, they absorb and scatter, carving the dark lane that divides the central light. In the infrared, they shine, re-emitting what they have taken in and outlining the ring as a bright band at longer wavelengths. Composition and size distribution determine how strongly they interact with light and how quickly they heat and cool. The Sombrero's grains follow extinction laws similar to those measured in other spiral galaxies, indicating mixtures of silicates and carbon-based particles with a range of sizes from very small molecules to sub-micron solids. The dust-to-gas ratio trends higher toward the centre, in step with metal enrichment, and falls outward with the thinning column. A lesser-known detail emerges when the mid-infrared spectrum is examined in detail. Features associated with complex carbonaceous molecules, the kind that carry distinctive bands in this regime, are present, but not as prominent as in some intensely star-forming spirals. The ratio between these bands and the broader featureless glow from warm dust shifts with radius in the ring. The bands strengthen where small grains survive under a moderate radiation field. Nearer the bulge, they fade as harsher light alters or destroys the most delicate carriers. This pattern provides a quiet diagnostic of the interstellar environment, not dramatic enough to change the galaxy's overall colour, yet sensitive to the balance between starlight grain processing and the cycling of matter through clouds. Energy flows through the medium along several channels. Starlight from old and intermediate age populations supplies a steady diffuse heating that warms dust and the warm phases of gas. Young stars, where they appear in patches inside the ring, carve small pockets of higher temperature and gentle ionization, but their spheres of influence remain local. Supernovae are infrequent compared with more vigorously star-forming galaxies, yet they occur often enough over millions of years to stir the gas and inject hot plasma that rises in buoyant loops. Magnetic fields thread these layers and guide the expansion of hot bubbles and the drift of cosmic rays, while also helping to support the gas against self-gravity in the vertical direction. The overall result is a layered atmosphere in quasi-equilibrium energy input, balanced by radiation expansion and mixing with the balance tilted towards calm by the Sombrero's low present rate of massive star formation. Kinematics and stability link the phases to the galaxy's structure. The measured rotation curve shows that circular motion dominates over random speeds across much of the disk, and that the shear between neighbouring rings of gas is gentle. Under these conditions, the parameter that gauges the susceptibility of a rotating disk to collapse remains high in many locations, a sign that large-scale gravitational fragmentation is suppressed. The bright central bulge contributes to this by deepening the potential well and by increasing rotational speeds at small radii, which tends to stabilize gas against forming long, bright spiral arms. Where density waves do exist, they are weak, gathering gas into the ring and nudging it inward and outward along nearly circular paths rather than piling it into narrow filaments. The hot diffuse component at the top of the disk connects the interstellar medium to the halo. X-ray observations detect a faint glow that rises above the plane and extends into the galaxy's broader atmosphere, a record of plasma at temperatures of millions of degrees. In the Sombrero, this hot phase is not bright yet. It is present as a thin skin that cools slowly and settles back toward the plane over long timescales. It carries heavy elements that were forged in earlier generations of stars and distributed by winds and ancient supernovae. As this gas radiates and mixes downward, it contributes to the metal content of the cooler phases, maintaining the gradient that rises toward the center and ensuring that new stars forming in the ring inherit a composition modestly enriched over the primordial baseline. Despite this coherent picture, an unresolved mystery remains in the persistently low rate of star formation given the availability of cold gas in the annulus. Several explanations are consistent with present data, but none is definitive. The bright bulge may raise the stability threshold and prevent gas from collapsing into bound clouds on large scales. The lack of a strong bar may limit radial inflow and compressive forcing that in other galaxies drives nuclear starbursts. The vertical pressure from the combined weight of stars and dark matter may keep clouds thin and resilient against fragmentation. Minor tidal stirring in the distant past may have heated the disk just enough to leave it resistant to new structure. Each factor could contribute, and their combination may hold the ring at a state where clouds form slowly collapse, only in small pockets, and disperse without igniting widespread activity. On planetary scales, the interstellar medium would define everyday conditions in subtle ways. In the ring, where dust columns are higher, stars' neighbours would look slightly redder and dimmer than their intrinsic colours, and the night sky would carry a soft glow in the far infrared from warmed grains. Interstellar polarization would trace the orientation of magnetic fields as aligned grains preferentially absorb and emit light along certain directions, producing a faint ordered signature in starlight measured through modest instruments. The density of interstellar gas around a planetary system would be low enough to leave heliospheres intact over long intervals, yet variations in the large-scale environment could slowly modulate their sizes as clouds drift past. In the outer disk beyond the ring, where the dust-thin stars would appear cleaner, and the infrared background would ebb, and the dark above the plane would deepen into the halo's quiet. Over longer spans, the medium cycles material between phases. Mass lost by aging stars enters as warm gas cools into the neutral layers and sometimes reaches molecular densities in shadowed niches. Radiation from newly formed stars reverses that path locally, breaking molecules apart and heating the surroundings. Rare supernovae close the loop by injecting hot gas that rises and later condenses. Throughout, dust grains grow by accreting atoms in cold clouds and shrink by sputtering in hot plasma, maintaining a steady size distribution that drifts only slowly. In a galaxy without strong external forcing, this cycle proceeds at a measured pace and writes a gentle record into the chemistry of each phase. Viewed as a system, the Sombrero's interstellar medium is a mediator between gravity and light. It carries the imprint of the potential set by bulge disk and halo. It filters and reprocesses radiation from billions of suns. It parcels out star formation in small doses, and it bridges the luminous regions and the hot, faint atmosphere that binds them to the outskirts. Its quiet is not emptiness, but balance. In the absence of strong tides and crowding the phases, find a long-lived arrangement in which cold clouds survive, warm layers circulate, and hot plasma breathes lightly into the halo. This is the context in which the denser molecular clouds of the next region take shape and weight anew, holding the cold that allows new stars to form without disturbing the calm outline of the galaxy's light. Within the Sombrero Galaxy, the coldest material gathers into molecular clouds, opaque bodies of gas and dust whose temperatures sit only a few tens of degrees above absolute zero. They prefer the dark annulus that encircles the bright bulge, because there the pressure, shielding, and gentle kinematics allow molecules to survive. Seen from Earth, the ring appears as a narrow lane that splits the central light, yet within that lane the medium is thick with small cold regions and a sparser background of cooler atomic gas. The consensus picture holds that stars in this galaxy now form mainly, though quietly, within these clouds as gravity overcomes internal motions in the densest pockets and creates new suns at a measured pace. Astronomers infer the presence of molecular hydrogen not by direct light, for that molecule is shy in the cold, but through companion species that radiate in the radio band. Carbon monoxide is the most common of these traces. Its lines glow when gas is cold and dense enough to be shielded from harsh radiation, but not so thick as to trap all energy. In the Sombrero, maps of carbon monoxide outline an annulus that coincides with the dust lane and stretches partway into the outer disk, with the highest intensities where the ring is most opaque in visible light. The velocities measured from these lines follow the ordered rotation of the galaxy, with only small departures caused by local streaming motions along weak density waves. This coherence is a major stable feature of the system. The ring turns as a calm belt rather than a tangle of colliding streams. Inside the annulus, clouds range from small transient clumps to larger bound entities that last for many orbital crossings. Their internal line widths indicate a mixture of thermal sound speed and gentle turbulence with modest magnetic support that helps resist collapse. The typical cloud is far less massive and less luminous in star-forming traces than the giant complexes found in the busiest spirals. This is not because the Sombrero lacks gas, but because the conditions for large-scale compression are not as strong. The bright bulge deepens the central potential and stabilizes orbits. The shear between neighboring paths is smooth, and the rate of cloud-cloud encounters is low. The result is a molecular medium that persists rather than burns quickly, a reservoir that feeds only pockets of star formation at any given time. A lesser-known detail arises when lines from denser gas tracers are measured. Transitions that require high densities, such as those from hydrogen cyanide or formylcation, appear weaker in the Sombrero than in more active galaxies once the overall molecular mass is taken into account. This pattern suggests that only a small fraction of the molecular gas sits at densities where rapid star formation proceeds. The bulk remains in a lower density state, cold and molecular but not tightly packed. The ratio between dense gas tracers and carbon monoxide becomes a quiet diagnostic of the ring's state. It points to a medium that leans toward preservation rather than production. In the same regions, mid-infrared features from aromatic carbon molecules are present, yet they remain modest near the bulge where stronger radiation alters the smallest grains. The conversion between tracer light and true mass also carries uncertainty. To turn a brightness in carbon monoxide into a column of molecular hydrogen, one adopts a factor that depends on metallicity, radiation field, and cloud structure. In bulge-dominated systems like the Sombrero, that factor may differ from values calibrated in the Milky Way's disk. A conservative reading keeps the total molecular mass within a range that admits these variations. Even at the high end of that range, the ring's gas would sustain the current calm rate of star formation for times much longer than a galactic year. This cushion matches the observed steadiness. The Sombrero shows no signs of a recent starburst, no large shells from widespread supernovae, and no heavy ionized outflows from the annulus. Cooling and heating in the molecular zone are balanced delicately. Dust grains cool clouds by radiating in the far infrared. At the same time, the diffuse starlight of old populations and the local radiation from young stars where they exist provide gentle heating. Cosmic rays, the high-energy particles that thread the disk, ionize the interiors and set chemistry in motion. The end state is a set of temperatures low enough to keep molecules intact and motion slow, yet not so low that the clouds collapse everywhere. Gravity wins only in the densest cores where local shielding is deepest and where external shear is weakest. There, over spans of a few million years, gas falls inward and new stars ignite while much of the surrounding material drifts on. The ring's geometry shapes this cycle. Its near-circular form and small vertical thickness confine clouds to a narrow band in radius and height. Weak orbital resonances associated with the inner mass distribution may gather material at the ring's characteristic radius, supporting a slow circulation in which gas drifts inward slightly on one side of a resonance and outward on the other. Over long times, this movement acts like a conveyor, bringing fresh material into zones where clouds can form, then carrying enriched gas back outward after stars shed mass. The process is quiet enough that the ring retains its smooth outline in integrated light. Star-forming patches appear as small scattered knots in ultraviolet maps rather than as long bright arms. Despite this coherent picture, an unresolved mystery remains at the heart of interpretation. Why is the star formation efficiency so low given the available cold gas? Several mechanisms likely contribute. The bright central bulge raises the threshold for instability and keeps large regions above the level where gravity can break them into bound fragments. The lack of a strong bar limits radial inflow and the shocks that often compress gas in other galaxies. Magnetic fields and mild turbulence provide additional support that slows collapse. The slow vertical oscillation of gas through the mid-plane reduces the rate at which clouds collide and merge into larger units. Each factor is plausible and has observational support in other systems, yet the exact balance among them in the Sombrero is not fixed with precision. Future measurements that trace dense gas and magnetic geometry in finer detail may narrow the range of explanations, but for now, the calm persists as a measured fact rather than a fully solved equation. Chemistry within the clouds proceeds along familiar lines. Carbon and oxygen join in carbon monoxide. Nitrogen, oxygen and carbon form small ions and simple molecules that mark different densities and temperatures. Dust grains provide surfaces where atoms meet and bond. As clouds age, they grow mantles of ices, water, carbon dioxide, and more complex species in their coldest interiors. When a young star ignites within a core, its light evaporates the nearest ices and drives a small local chemistry that returns molecules to the gas phase. In the Sombrero, these lively zones are fewer and dimmer than in gas-rich spirals, but they exist in modest numbers within the ring. Their output blends into the wider glow and contributes to the steady low level of newborn starlight that freshens the disk without changing its calm character. Kinematics support the picture of measured evolution. Molecular lines show dispersions that stay below the speeds typical of strong spiral shocks. Gradients across individual clouds are small, consistent with gentle shear. The rotation of the ring sets a long clock for every process a cloud completes a circuit in hundreds of millions of years, while its internal life is counted in millions. Under such conditions, feedback from young stars winds light and occasional supernovae sculpts only their birthplaces and does not stir the annulus as a whole. The gas that escapes these local bubbles cools and returns to the cold phase, closing the loop without driving large fountains into the halo. The halo's hot atmosphere remains present but thin, and it barely brushes the ring except through a slow exchange of energy across its topmost layers. On planetary scales, a star system embedded within a sombrero cloud would know a dimmer, redder sky. The central bulge would still rise split by the dark lane, but its light would be sifted by dust into a soft brownish glow. Nearby stars would appear as warm embers behind veils visible more clearly in the infrared than in the blue. Instruments would record a stronger far infrared background from heated grains and a mild increase in polarization from aligned elongated dust particles that trace magnetic fields. Cosmic rays would set a quiet ionization in the cloud's gas, shaping the chemistry of thin atmospheres on outer cold worlds. On timescales of seasons and years, nothing dramatic would change. On timescales of millions of years, the cloud would drift, compress in places, and perhaps give birth to a few small clusters each with a handful of bright young stars before the region relaxed again. Stepping back to the scale of the ring, the role of the molecular medium becomes clear. It is the bank in which the galaxy stores the raw material for future stars, paying out interest slowly rather than spending principal in a burst. It filters starlight cushions the disk against sudden change, and maintains a reservoir that can respond if internal dynamics or some distant gentle tide ever shift. Its present calm is a feature, not a pause, and it explains much of the sombrero's quiet face, an annulus of darkness that is in fact dense, cold, and luminous in wavelengths that human eyes cannot see. As the inward path continues, the view will leave this belt of cold gas and encounter the subtle patterns of spiral structure that shape the starlight just inside the ring, where ordered motion and faint arms arrange the old stars into curves that echo a spiral's form without the clamour of a grand design N. Inside the dark annulus, the Sombrero Galaxy shows faint patterns in starlight that suggest spiral form without loud contrast. The view from Earth is nearly edge-on, so any arms lie foreshortened into the narrow band that crosses the bulge. Yet their presence can be inferred from subtle modulations in surface brightness, and from the way dust lanes curve as they approach the inner regions. The consensus picture is that the sombrero hosts weak, tightly wound spirals, or ring-like segments that guide gas and stars along gently varying paths. These structures are not the grand, high-contrast arms seen in many nearby disks. They are low-amplitude waves in density that help organize material and set the rhythm for small pockets of star formation while leaving the overall light distribution smooth. Their existence aligns with the galaxy's bright bulge and quiet environment. In systems where the central mass is large and tides are mild, density waves can persist at low amplitude over long spans, adding order without carving dramatic lanes. Kinematic maps support this view. Spectra across the disk show small coherent departures from pure circular motion, the kind expected when stars and gas respond to a weak spiral potential. These streaming motions tilt orbits slightly and produce recognizable signatures velocities, rise a little on one side of a crest and fall on the other, and gas lines show tiny phase shifts relative to stellar absorption features. The amplitude of these shifts is small, consistent with a pattern that does not shock the gas strongly. Where the dust ring meets the inner disk, the lanes bend in a way that matches a tightly wound arm geometry with pitch angles narrow enough that the features almost close into a ring. This is a common outcome when a large bulge shapes the inner rotation curve. The rapid change in orbital speed with radius compresses patterns into tight spirals and favours resonances that collect gas near specific radii. Light at different wavelengths traces the same shape with different emphasis. In the optical band, the pattern appears mainly as gently brighter and fainter streaks in the inner disk, once the strong extinction from the outer lane is accounted for. In near-infrared light, where dust effects are weaker, the underlying stellar mass distribution shows the same wave with slightly higher clarity, a sign that the structure is not only a feature of young stars but a modulation in the old stellar background itself. Ultraviolet images add small scattered knots along these curves, indicating places where gas was compressed enough to form short-lived blue stars. None of these contrasts is strong. Taken together, they outline a stable low-contrast spiral field that acts more as a guide for motion than as a driver of major star formation. A lesser-known detail arises from the asymmetries between the two sides of the disk. Deep images show that the brightness along the major axis is not perfectly symmetric about the centre once the dust lane's extinction is modelled away. One side appears slightly enhanced at certain radii, and the curve of the inner dust features shows a small offset relative to the opposite side. These lopsided signatures are common in disk galaxies and often point to minor perturbations, a long-lived M-1 mode in the mass distribution, a small misalignment between disk and halo, or a mild memory of past accretion that has not fully mixed. In the Sombrero, the asymmetry is gentle and steady, not a transient warp or a prominent tidal tail. It suggests that the galaxy carries a slight internal imbalance that shifts the crest of the spiral pattern by a small angle, an effect that can persist for many rotations without growing into strong structure. In the inner disk close to the bulge, resonances set by the rotation curve can collect stars and gas into rings and pseudo-rings. Measurements in the Sombrero indicate a preferred radius where such a feature emerges just inside the main dust annulus, and along this radius the faint spiral segments nearly close. The gas shows a narrow spread in velocities here, and the dust lanes align along the same path. This matching points to a dynamical resonance that traps or slows material, raising its density enough to change the local light distribution. The feature is not a starburst ring. It is a modest enhancement that fits the galaxy's low present rate of star formation. Its significance lies in how it links the outer reservoir to the inner architecture. Material guided by the weak spiral and by oval distortions collects near this radius, and either lingers or leaks inward, slowly feeding the very inner regions without large shocks. The presence or absence of a bar is part of this story. Strong bars often drive clear two-armed patterns and channel gas toward the centre. In the Sombrero, evidence for a strong extended bar is limited. Near-infrared views and kinematic studies suggest only a mild inner oval or small bar-like distortion. Such a feature can still see tightly wound spirals and set resonances, but it does so with less forcing than a long bar. The outcome matches what is seen a system where patterns exist and matter moves along them, yet the contrasts remain low and the inflow is slow. This is consistent with a galaxy that has kept its disk cool and ordered while avoiding major distortions from environment. An unresolved mystery concerns the origin and longevity of the lopsidedness and the exact strength of the spiral pattern. One path to mild asymmetry is a recent small accretion of a satellite whose stars and gas have already dispersed. Another is a natural mode excited by internal processes that can persist for many giga-years. The first option would leave traces in the outer halo and globular cluster system, some of which are present as faint streams and number gradients. The second would not require external triggers and would arise from the disk and halo interacting through gravity in a way that sets a one-sided wave. Current data allow both readings. The pattern speed of any inner oval is also not known to high precision, and with it the exact locations of resonances carry some uncertainty. Better constraints on these quantities would sharpen the dynamical picture and fix how gas flows across the boundary between ring and inner disk. Viewed from within, the spiral modulation would be gentle, A planetary system orbiting in the inner disk would pass through slightly denser and slightly rarer regions over tens of millions of years. The difference would not be dramatic in starlight. It would appear as small changes in the density of faint stars on the sky, and as mild variations in the number of nearby clouds. Dust lanes would curve across the sky with a steady geometry, and the central bulge would remain the dominant beacon still cut by the outer lane. The local interstellar medium would feel modest shifts in pressure as the system drifted across a crest or trough, changes enough to modulate cloud formation on long timescales, but not enough to alter planetary environments quickly. In this way, the spiral field would influence climate only through very slow background effects, tied to the distribution of gas and dust. Small non-circular motions near the arms also shape how gas converts into stars. Where gas meets a spiral crest, compression raises density and can push a parcel across the threshold needed to form bound cores. In the sombrero, the weak amplitude of the wave means that only a fraction of the gas crosses that threshold at any time. Many parcels are simply redirected along the crest and then released into the following trough with their state unchanged. This picture matches the low conversion efficiency measured in the ring and inner disk. It also explains the scattered nature of young stars, which appear as small knots rather than long chains. The vertical structure of the pattern is quiet. In some galaxies, strong arms puff up the disk locally by stirring random motions. Here, the measured dispersions remain modest. The thin stellar component stays thin into the inner regions, and any thick component contributes only a smooth background with little response to the weak spiral. This stability helps maintain the sharp outline of the dust lane against the bulge and keeps the inner disk smooth in projection. It also limits the mixing of stellar populations across heights, preserving the mild gradients in colour and chemistry that run from plane to halo. A lesser detail of technique is worth noting. Because the galaxy is almost edge on separating true spiral structure from projection effects requires models that combine photometry with kinematics. Analysts fit the two-dimensional light distribution with components for bulge, disk and ring, then look for residuals that trace curved enhancements. They compare these residuals with velocity fields, looking for the phase shift expected when gas and stars respond to a wave. Applied to the sombrero, this method yields internally consistent patterns with small pitch angles that repeat on both sides of the center with slight asymmetry. The alignment of dust gas and stellar light across methods strengthens the case that the inner disk hosts real though weak spiral features. These structures connect the outer belt of cold gas to the brighter inner architecture. They organize slow inflow and outflow across resonant radii, distribute angular momentum and shape where new stars appear. They also modulate the appearance of the galaxy in subtle ways that only careful analysis reveals. In a system dominated by a luminous bulge and set in a calm environment. This is the expected form of spiral structure, a low contrast pattern that lasts, moves mass quietly and leaves the disk largely undisturbed. The sombrero's faint spirals and mild asymmetries fit that expectation and help explain why the galaxy presents such a steady face in integrated light. As the path moves one step further inward, these patterns give way to the rising dominance of the inner dynamics, where the rotating field tightens and the bright central bulge takes fuller control of orbits. The starlight of the Sombrero Galaxy carries a layered record of time and chemistry, a mixture of very old populations in the bright bulge, older and intermediate age stars in the inner disk, and a still older, thinner population in the outskirts and halo. Spectra taken across these regions show absorption features that strengthen and fade with age, and composition bands from magnesium and iron in the optical, the broad calcium triplet in the near-infrared, and a smooth continuum that reddens as hot blue stars become rare. The consensus view is that the bulge assembled early and rapidly, producing a dense population of old metal-rich stars, with an enhancement in the so-called alpha elements, oxygen, magnesium, silicon, and their kin relative to iron. Such an enhancement points to brief, intense episodes of star formation dominated by the explosions of massive stars which enrich alpha elements quickly, before slower processes in lower mass stars contribute iron on longer timescales. The disk, by contrast, shows slightly lower metallicity and a more extended enrichment path consistent with star formation that trailed off gently and continued at a low rate to the present. Together, these tendencies set shallow gradients. Heavy element abundance rises toward the center, and the average stellar age rises with it. Yet no sharp discontinuities break the profile. In the bulge, the light is dominated by stars older than roughly 10 to 12 billion years. Their spectra show strong magnesium features and a red continuum that matches a population long past the peak of star birth. The metal content is high by galactic standards, indicating that gas in the central regions was enriched quickly and retained efficiently. The presence of many red giant stars, asymptotic giant branch stars and their descendants adds a soft infrared glow that blends with dust emission from the ring. Kinematic studies show that these bulge stars move with large random speeds, superposed on slow rotation, a sign of a deep potential well, and an early violent relaxation era that mixed orbits. The chemistry and kinematics agree. A central population that formed fast became chemically rich and then evolved quietly, while the disk continued to add stars at a far lower pace. The inner disk reflects a quieter history. Its integrated colours are still warm but not as red as the bulge, and its spectral features imply a mixture of ages. Intermediate age stars, those born a few billion years after the bulge's main epoch, add a modest contribution, while the present-day star formation adds only a faint blue frosting. This combination produces smooth colour gradients from bulge to disk, once dust extinction is corrected for line-of-sight effects. Heavy element abundance declines gently with radius levelling into the outer disk, where enrichment is slower and less complete. The gradient is mild compared with those in gas-rich, strongly barred spirals, consistent with a system where large-scale inflows and outflows have been limited, and where the ring has long regulated exchange between inner and outer regions. A lesser-known detail emerges at ultraviolet wavelengths. Despite its old age and low present star formation, the bulge shows a mild ultraviolet upturn, a surplus of far ultraviolet light compared with what would be expected from an elderly cool population alone. This feature, familiar in massive elliptical galaxies and bright bulges, is usually traced to a small minority of very hot low-mass stars in late evolutionary stages, such as extreme horizontal branch stars or their immediate descendants. In the Sombrero, the upturn is modest, yet it appears clearly when dust attenuation is accounted for, and it adds an austere blue prickle to the otherwise red spectrum of the central light. Its presence supports the picture of a very old population with particular chemical histories that permit such stars to form, and it offers an additional independent sign that the central regions have aged in place for most of cosmic time. Across the galaxy, elements beyond hydrogen and helium, astronomers group them as metals follow patterns set by star formation and gas flows. The alpha to iron ratio is higher in the bulge than in the disk, a signature of rapid early enrichment by massive stars. Iron rises more slowly with time as long-lived stars die and seed the interstellar medium with their products, so the disk, which formed stars over longer spans, shows a closer balance between alpha elements and iron. Planetary nebulae in the inner halo offer another probe. Their emission lines reveal oxygen and neon abundances that sit between bulge and outer disk values, implying that the halo's visible stars come from both early in situ formation and the gentle accretion of small companions with slightly leaner chemistries. In this way, individual objects serve as beacons in the chemical map, tying the ensemble picture to discrete measurable sources. The dust content tracks metals as well. Grains grow more plentiful and complex toward the centre, where enrichment is highest and where dying stars continually supply raw material. Carbon-rich and silicate grains both appear with size distributions that shift subtly with radius as shocks, radiation and growth in cold clouds reshape the population. Asymptotic giant branch stars in the bulge. Elder suns, shedding their outer layers, contribute dust that later mixes into the ring and disk, raising the opacity locally and feeding the cycle of grain growth. The result is a coupling between chemistry and appearance. Higher metallicity supports more dust. More dust deepens the dark lane against the bulge and brightens the ring at infrared wavelengths. An unresolved mystery threads these patterns. How quickly and by what exact sequence did the bulge reach its great mass and chemical richness relative to the disk? The alpha enhancement implies a short formation timescale, but that constraint alone does not fix whether the central star formation surged because of an early dissipative collapse of gas, a brief era of gas-rich mergers that left the disk able to reform, or a combination of both. The near absence of strong scars in the present disk favours events that happened very early, or with small mass ratios yet lingering streams in the halo, show that minor accretion persisted. The precise timeline within the first few billion years after the Big Bang remains open. High-resolution models can reproduce the present chemical gradients through multiple channels, and current observations do not prune the tree of histories to a single branch. The mild ultraviolet upturn adds a further twist because its strength depends sensitively on metallicity and on specific late evolutionary pathways that are still being refined in stellar models. The initial mass function, the statistical Thal spread of stellar masses at birth, also touches interpretation. If the bulge formed with a mix similar to that inferred in the Milky Way's disk, then its present chemical state points to very efficient early star formation in a deep potential. If, however, the central regions favoured slightly more massive stars at birth, then alpha elements could have been produced even faster, requiring less total time to reach the observed ratios. Observations in other galaxies hint that the central mass function can vary with environment, but direct constraints in the Sombrero are indirect and model-dependent. This uncertainty feeds into questions about how quickly the central black hole grew, how the bulge's light relates to its mass, and how feedback from old and young stars regulated the supply of gas to subsequent generations. At the scale of single stars, chemistry leaves fingerprints beyond broad indices. Sodium and nitrogen lines in bulge spectra sometimes appear stronger than simple models predict a common trend in dense old populations. Such enhancements can arise from multiple stellar generations within clusters that later contributed stars to the bulge, or from subtle biases in the mass function of long-lived giants. In the Sombrero, these features are mild, yet they help anchor the idea that the bulge gathered material from many building blocks, including massive clusters, and processed it under conditions that differ from the thin disk. Meanwhile, in the outer regions, measurements of metallicity through planetary nebulae and giant star colours suggest a wide spread of values at a single radius. The hallmark of a population built partly by accretion from small satellites with varied histories. On planetary scales, the chemistry of the galaxy sets the inventory from which planets form. The high metal content in the bulge and inner ring means that solid building material, iron, silicates and ices is abundant in those regions, which supports the formation of rocky worlds and the cores of giant planets. In the outer disk and halo, where metallicity wanes, the typical initial stock of heavy elements declines, shaping the types of planetary systems that can assemble. These are general tendencies rather than strict rules, yet they tie the broad chemical gradients to the composition of distant worlds. A planetary sky within the ring would thus shine through a medium rich in dust and metals reddening starlight and adding a faint infrared background. A planetary sky at the outer edge would thin and cool with cleaner starlight and fewer heavy elements in local gas. In both settings, the galaxy's slow evolution would leave the night stable for spans far longer than any planetary climate cycle and chemistry would change only as new generations of stars return processed material to the medium. Taken together, the Sombrero's stellar populations and chemistry form a coherent yet gently varied map. The bulge is old metal rich and alpha enhanced. The inner disk is slightly younger, with lower metallicity and continued low-level star formation. The outer disk is older and leaner in heavy elements. The halo blends contributions from early in situ stars and long-ago companions. Lesser features like the modest ultraviolet upturn and mild line enhancements provide texture without breaking the overall calm. Uncertainties remain about the pace and path of early assembly, about the subtle shape of the initial mass function in the centre, and about the degree to which minor accretions seasoned the outskirts. Yet the broad narrative is steady, a galaxy that built a bright, chemically mature heart early and then evolved inward from a metal-poor boundary filling in layers of stars whose compositions record distance from the centre as clearly as position on the sky. The result is the quiet, layered glow that defines the Sombrero's face and guides the path further inward toward the realm where dynamics tighten and orbital families reshape how light gathers around the core. Within the inner disk of the Sombrero Galaxy, orbits tighten, and patterns become more strongly shaped by the central mass. The bright bulge raises circular speeds sharply over a small change in radius, and that gradient organizes stellar families into distinct behaviors. Gas follows nearly circular paths with small systematic departures near weak resonances, while older stars carry a blend of rotation and random motion that thickens slightly toward the center. The consensus view is that this region is dynamically hot compared with the outer disk, yet still ordered. Rotation dominates, shear is smooth and non-circular, streaming remains modest. The rotation curve climbs from the ring inward, reaches a gentle plateau and then eases toward the nucleus where the potential becomes nearly spherical. In such a field, orbital families separate into those that align with any mild inner oval, and those that cross it orthogonally, and gas gathers near preferred radii where the frequencies of motion meet simple ratios. Kinematic maps in the near-infrared less affected by dust trace the stellar velocity field along the major and minor axes. They show that stars in the inner disk rotate swiftly, but lag the gas by a small amount because of asymmetric drift, the dynamical correction produced by their random motions. Velocity dispersions increase toward the bulge, turning the inner disk into a zone where stars orbit in a slightly thicker layer than in the outer sheet. The line profiles broaden accordingly, and higher-order moments indicate gentle departures from purely Gaussian shapes, signs of a mix between warm disk orbits and the hotter bulge component. Gas lines paint a complementary picture. They stay narrow, follow a cleaner rotation, and display only small S-shaped twists that reveal weak streaming along tightly wound spirals or an inner oval. Together, these signatures anchor a widely accepted picture of an inner disk guided by a deep, nearly axisymmetric potential with only a faint non-axisymmetric perturbation. Resonances set the rhythm. As circular speed rises toward the center, the frequency of small radial oscillations around circular motion also changes. Where the difference between these frequencies and the pattern speed of any inner oval takes special values gas tends to collect. Observations of the Sombrero's light distribution reveal a preferred radius just inside the main dust annulus, where the inner disk shows a faint, nearly closed ring in starlight and dust. This radius is a plausible location for an inner resonance where material lingers and where weak spiral segments appear to join. Inside this region, the gravitational pull of the bulge becomes dominant and stable orbits pivot from those elongated along the oval to those oriented at right angles to it. The transition softens any bar-like distortion that might exist, limiting its reach and keeping non-circular motions low. A lesser known detail arises in the subtle shape of isophotes, the contours of equal brightness. In deep high-resolution images, the innermost disk shows a lens-like zone with nearly constant surface brightness over a narrow span of radii, a feature sometimes associated with dissolved or very weak bars. Such lenses can form through long steady evolution, when stars trapped by an oval pattern slowly diffuse, leaving behind a smooth flat profile that bridges disk and bulge. In the sombrero, this inner lens is faint and easily masked by the bright central light, yet careful decomposition recovers it. Its presence supports the view that any bar-like structure is mild and that secular processes have had long time to round it, consistent with the galaxy's calm environment and the stabilizing influence of the massive bulge. The inner disk's stability can be expressed in simple physical terms. The balance between self-gravity random motions and shear sets where the gas will fragment into long filaments and big clouds. Measurements suggest that the threshold for collapse remains high across much of the inner disk, raised by strong rotation and vertical gravity from the bulge. As a result, density waves do not develop into vivid arms, and star formation appears only in small knots. The stars themselves respond differently. Their random motions keep them from gathering into sharp lanes, yet the weak non-axis symmetry can still rearrange their guiding centers slowly. Over billions of years, this radial migration blurs chemical gradients and spreads intermediate-age populations inward and outward by a few thousand light years without heating the disk dramatically. In a system like the Sombrero, such churning proceeds at a measured pace, leaving gradients shallow, but not erased. Gas inflow is gentle. In galaxies with strong bars, large torques drive rapid transport toward the centre, piling gas into bright nuclear rings. Here the torque is small. The faint inner oval and tightly wound spirals pass angular momentum only slowly, so gas drifts inward at low rates. Where it accumulates near the inner resonance, it can form a narrow, low-contrast star-forming ring that adds young stars to the inner disk without igniting a burst. The lack of conspicuous shocks in gas lines supports this quiet flow line. Widths are narrow. Excitation diagnostics show mild heating rather than strong shocks, and there is no evidence for thick dust lanes offset from a strong bar features that would signal vigorous streaming. Despite this coherent picture, an unresolved mystery remains in the exact strength and pattern speed of any inner oval or small bar. Different modelling approaches using light profiles and gas flow prefer slightly different pattern speeds, and each speed shifts the resonant radii by a small amount. Because the galaxy is so nearly edge on, projection effects amplify small uncertainties in deprojected shape. As a result, the degree to which secular evolution has already transformed the inner disk, whether the lens is the remnant of a once stronger bar or the product of long, weak oval forcing, cannot yet be fixed with confidence. Better measurements of higher order velocity and moments and improved reconstruction of the three-dimensional shape may narrow the range, but for now both histories remain consistent with the data and with the galaxy's broader calm. The vertical structure ties the inner disk to the bulge. As one moves inward from the ring, the thin stellar layer thickens gently, not as a separate discrete component, but as a smooth rise in scale height, driven by the deepening potential and by accumulated random motions. This thickening is modest. It does not reach the puffed height associated with strong buckling instabilities in barred galaxies. The absence of boxy or peanut-shaped isophotes in the central light argues against recent buckling and supports a classical round bulge that dominates the shape. Gas remains even thinner than stars and hugs the plane, a sign that turbulence and magnetic support are low and that vertical gravity is strong. On planetary scales inside the ring, the sky would show the bulge as a vast bright dome, with the dark lane still present but shallower. Dust extinction would lessen compared with the ring, and the stellar background would intensify, raising the diffuse optical glow. The inner resonance, if occupied by a low-contrast ring of gas and young stars, would paint the sky with a sparse sprinkling of blue clusters along a narrow band. The rotation field would set long, predictable drifts in the positions of these clusters over tens of millions of years, a motion too slow to alter night-to-night appearance, but steady over geological time. The interstellar medium would be warmer and thinner than in the ring, and the far infrared background from dust would fade compared with the midplane just outside. The inner disk's energy flow threads quietly through many channels. Starlight from the dense bulge pervades the region and heats dust grains that survive in the plane. Occasional supernovae from scattered star formations stir small bubbles that rise and merge into a thin hot skin. Magnetic fields guide the expansion of these bubbles, but remain too weak to imprint large filaments. Cosmic rays diffuse along the field and add a small uniform pressure. None of these processes rivals gravity and rotation. They decorate the dynamics rather than drive it. Their cumulative effect is to maintain a layered atmosphere in which gas cycles between warm and cold phases, without strong fountains or winds. A second lesser-known detail concerns the shape of the stellar velocity ellipsoid, the three directions that describe random motions. In many disks, the ratio between radial and vertical dispersions changes with radius reflecting how stars heat over time. In the Sombrero's inner disk, this ratio remains relatively high in the plane and lower vertically, a configuration that keeps the layer thin and stable, and that hints at slow, steady heating dominated by spiral waves and molecular cloud scattering rather than by sudden events. The pattern mirrors the galaxy's history. Small cumulative processes leave a smooth footprint. Secular evolution knits these elements together. Over long spans, the weak oval and spirals redistribute angular momentum. The inner lens remains or grows slightly, as trapped orbits diffuse, and the faint ring at resonance continues to trade gas with adjacent radii. Chemical gradients soften as stars migrate a little. The bulge's dominance persists and keeps the pattern from strengthening. If the inner oval were to gain power, the disk could develop stronger streaming and a brighter ring. If it were to fade, the lens would become even more featureless. The present state sits between these outcomes, stable enough to last and active enough to maintain slow change. In sum, the inner disk of the Sombrero is a realm where gravity from a massive bulge imposes order, where rotation leads and random motions follow, where resonances shepherd gas into narrow paths, and where weak non-axis symmetry modulates the flow without disrupting it. The consensus features are clear: a rising inner rotation curve, modest asymmetric drift, narrow gas lines, a faint inner ring or lens, and tightly wound spiral traces. The open questions involve the exact pattern speed and the strength and origin of the mild oval details that matter for reconstructing the earliest steps of secular reshaping. On the scale of worlds, the result is a sky brighter and cleaner than in the ring, a plane where stars crowd closer on the eye yet move with a calm that changes landscapes only over times as long as continents endure. The central bulge of the Sombrero Galaxy rises like a luminous sphere that overwhelms the inner view, a smooth concentration of old starlight whose gravity sets the pace for everything around it. In projection, it fills most of the galaxy's apparent diameter, pressing outward against the dark rim of the ring and the thin wash of the inner disk. Its surface brightness climbs steeply towards the centre, and its contours stay round with only a gentle flattening along the plane where the disk cuts through. The consensus view is that this is a classical bulge, a dynamically hot, centrally concentrated structure that formed early and rapidly, now supported mainly by random stellar motions rather than by rotation. Its presence explains the galaxy's bright core, the sharp rise in circular speed within the inner kiloparsecs when measured in relative terms, and the way resonances shape the inner disk into lenses and weak rings rather than strong open spirals. Spectra across the bulge bear the signatures of an ancient population. Absorption lines from magnesium and other alpha elements stand strong relative to iron, a pattern that points to a short, intense epoch of star formation dominated by massive stars whose supernovae enrich the gas quickly. The continuum is red and smooth, consistent with stars older than roughly 10 to 12 billion years, and with only a faint contribution from young populations. The mild ultraviolet upturn that peeks through dust attenuation adds a subtle blue edge at the shortest wavelengths, a trait common in old metal-rich systems, where a small minority of low-mass stars reach very hot evolutionary stages late in life. Taken together, these features draw a portrait in which the bulge assembled its mass and metals early, then aged in place, while the surrounding disk continued more slowly. Kinematically, the bulge is dominated by velocity dispersion. Stars move on orbits with many orientations, their paths crisscrossing to build a nearly round light distribution. Maps of the line of sight velocity field show some rotation aligned with the disk, but the amplitude is modest compared with the random speeds. This balance yields a flattening that is slight and an isophotal shape that remains close to elliptical without the boxy or peanut-like signatures associated with recent buckling of a strong bar. The inner disk thickens gently as it approaches the bulge, and the gas layer thins further under the bulge's vertical gravity, hugging the plane with narrow line widths that betray little turbulence. The result is a core where stars dominate the potential light piles up steeply, and the interstellar medium takes a quieter, more stratified form than in the ring. A lesser-known detail emerges when the bright central light is decomposed into fine structures. High-resolution imaging reveals a very compact, flattened stellar component embedded within the broader bulge, nuclear disk only a few hundred parsecs across when scaled by the galaxy's distance and geometry. This nuclear disk aligns with the main plane and carries a sprinkling of dust lanes that curve inward before fading into the glare. It rotates more rapidly than the surrounding bulge, and likely represents material that drifted inward over long times, settling into a thin configuration without amassing enough mass to alter the bulge's global character. Its existence shows that even a classical bulge can host a small cool subsystem fed by the faint inflow, guided by inner resonances and by the weak oval that shapes the inner disk. The component is subtle in integrated light, but becomes clear when dust is traced in absorption and when near-infrared images isolate the stellar mass field. Chemistry supports the central concentration of enrichment. Metallicity is highest in the bulge and declines outward into the inner disk, a gentle gradient that softens as stars migrate but remains visible after careful correction for dust. The ratio of alpha elements to iron climbs toward the centre, reflecting the rapid clock of early formation, and auxiliary indicators such as sodium and nitrogen lines hint at the contributions of massive clusters and multiple stellar generations to the bulge's mix. Dust content rises with metallicity, old mass losing giants, return rhodium and carbon and silicate grains to the local medium, which then drift outward to the ring or remain as a thin veil in the mid-plane. In the infrared, this veil warms under the bulge's radiation, adding a soft glow that blends with starlight and quietly brightens the inner few kiloparsecs in longer wavelengths. The bulge also anchors the dynamical resonances that govern gas paths. Its deep potential steepens the inner rotation curve, tightening pitch angles and encouraging the formation of nearly closed inner rings, where orbital frequencies meet simple ratios with any weak pattern speed. Gas collects there, forms stars in modest patches, and then either lingers or spills inwards slowly. The same central gravity raises the threshold against large-scale fragmentation, so spiral waves remain low in amplitude. In this way, the bulge acts not only as a mass reservoir, but also as a regulator, keeping the disk orderly and suppressing the instabilities that would otherwise build strong arms or fuel rapid central starbursts. Despite this coherent picture, an unresolved mystery remains in the exact path the bulge took to reach its present mass and structure relative to the disk. Two broad families of histories are consistent with current data. In one, a rapid dissipative collapse of gas in the young universe built the bulge swiftly, with the disk assembling more slowly afterward from later infall. In the other, a brief series of gas-rich early mergers stacked mass into the centre, while leaving conditions that allowed a disk to reform or survive, with the present calm secured once the environment quieted. Both paths can reproduce the observed alpha enhancement steep light profile and weak present-day non-circular motions. Both can coexist with the rich old globular cluster system that orbits the halo. Distinguishing them requires finer constraints on the inner orbital structure, on subtle asymmetries in the bulge's shape, and on the ages and chemistries of the very central stars, where the two scenarios might leave small differences. For now, the bulge's roundness and age favour an early intense formation, but the precise blend of collapse and merger remains open. The relationship between the bulge and the central black hole adds a further layer of uncertainty and interest that will come to the fore later. In many galaxies, the mass of the central black hole correlates with the velocity dispersion of the bulge, suggesting linked growth. The Sombrero's high dispersion implies a central mass that sits on the same general relation, and faint nuclear activity seen at high energies hints at a quiet but present engine. Yet the present accretion rate is low, and feedback from the nucleus appears too weak today to shape the bulge on large scales. Whether stronger episodes occurred early, helping to quench central star formation and seal in the bulge's old age, remains a topic where indirect evidence is weighed carefully, because direct memories of those times have faded in the stellar light. On planetary scales, the sky within or near the bulge would be dense with stars. The dark lane that bisects the bulge from our vantage would still be visible from worlds near the plane, but its contrast would soften as the line of sight through dust shortens inside the ring's radius. Above the plane, the view would open onto a radiant hemisphere of old stars whose combined light would brighten the night far beyond the levels seen from the outer disk. Individual red giants would stand out as steady warm points, and the far background of distant galaxies would be largely lost in the glare. The interstellar medium would be thinner and warmer than in the ring. So far infrared background from dust would drop slightly, while the optical and near-infrared glow of stars would rise. The frequency of subtle gravitational microlensing events would be higher than in the outskirts, as stars pass in front of one another along long sightlines, though such events would still be rare on human timescales. In dynamical terms, a planetary system in the inner bulge's influence would trace a path around the galaxy, with a shorter period than one in the outer disk, and with stronger vertical restoring forces. The local tidal field would be steadier and more intense, but close stellar encounters would remain uncommon, because stellar densities, while high in projection, are still sparse on the scale of planetary systems. Cosmic rays would diffuse through the bulge and halo, much as elsewhere, modulated by magnetic fields that thread the region without carving large filaments. The net effect would be a stable background light and a calm interstellar environment, punctuated only by occasional supernovae from the modest star formation in the inner ring, or by rare novae in old stellar systems. Over long times, the bulge changes little in appearance. Secular processes in the surrounding disk can move stars inward or outward by small amounts, and the faint nuclear disk can grow slowly as gas drifts toward the centre, and forms new stars in episodic trickles. These additions barely alter the bulge's global profile, which remains dominated by ancient stars and by the deep gravitational well that holds them. The minor flattening along the plane may increase or decrease subtly as the embedded disk gains or loses mass, but the overall roundness and steepness of the light remain. In the absence of strong external tides or major inflows, the bulge continues as a long-lived steady heart around which the ring and disk revolve. Thus the sombrero's prominent central bulge defines both the look and the order of the inner galaxy. Its old metal-rich stars set the colour and brightness of the core. Its strong gravity tunes the rotation curve and the resonances that shape the inner disk. Its round dispersion-supported structure marks it as a classical bulge formed early, and its quiet present allows fine substructures like the nuclear disk to persist without stirring the whole. What remains uncertain is the exact mix of early collapse and early merging that built it, and the degree to which the central black hole's past activity helped end its formative star formation. Even with these open questions, the bulge stands as the dominant architecture at small radii, a dense sphere of ancient suns whose steady pull guides the galaxy inward toward the more crowded compact region where the nuclear light rises and the innermost dynamics close around the core. At the centre of the Sombrero Galaxy, the light gathers into a compact nucleus embedded within the broader bulge, a region where stellar density climbs sharply and dust threads in narrow lanes that curve inward before fading into glare. The consensus view is that this nucleus is a composite environment, an old crowded stellar core, overlain by a very small flattened stellar disk and interleaved with thin ribbons of gas and dust that settle along the plane. Kinematics show rapid rotation for the innermost cool component and high random speeds for the surrounding stars, a pairing that marks the transition from the dispersion-supported bulge to a rotation-supported nuclear layer. Ionized gas appears in delicate emission near the centre, tracing a quiet field of photonization and mild shocks rather than the fierce turbulence of a starburst. Against this luminous background sits a compact hard-spectrum source detectable at high energies and in radio evidence of a low-level active nucleus that will be examined more closely when the central mass is addressed. The nuclear light is smooth on large scales, but reveals structure in fine detail. High-resolution images show dust filaments that arc across the inner few hundred parsecs, some aligned with the midplane and others tilted slightly as if they were the fossil wakes of clouds settling inward along inclined orbits. Between the filaments lies a flattened stellar component and inner disk that is only a fraction of the ring's radius and vastly thinner. It shares the main galaxy's orientation within a few degrees, and rotates swiftly, consistent with stars that formed from gas that drifted inward and cooled. The older stellar background, by contrast, shows little net rotation at the same radii, and dominates the surface brightness. Together, these components produce isophotes that are nearly round but carry a subtle lens, like flattening a signature easy to miss unless profiles are decomposed carefully. A lesser-known detail emerges from the nuclear star counts and colours. Within the central few tens of parsecs, the integrated light is dominated by very old populations, as in the bulge, but interleaved among them is a faint sprinkling of slightly younger stars that share the rotation of the nuclear disk. Their contribution to the total light is small. Their dynamical imprint is larger than their luminosity, because they define the coldest orbits at the very centre. In spectra, this minority emerges as weak Balmer absorption features and a slightly flatter continuum than expected from a purely ancient population. The implication is that the nucleus has accepted small additions of gas over long times and converted some fraction into stars, not in a burst, but in episodic trickles guided by inner resonances. The result is a nucleus that is overwhelmingly old yet not entirely fossilized. Gas in the nuclear zone is scarce but not absent. Emission lines of low ionization species appear at modest strength, consistent with a dilute warm medium bathed in a hard radiation field and occasional slow shocks. The geometry suggests that gas streams inward along the dust filament stalls near preferred radii set by resonances, and either forms stars inefficiently or continues to drift inward on near-circular paths. Line widths remain narrow, implying low turbulence, and the absence of strong broad components argues against fast outflows at present. The gas temperature, density and ionization state align with a picture in which the central engine is faint, the surrounding stellar radiation field is strong, and the mechanical energy input from recent supernovae is low. The nuclear region stability follows from the surrounding mass. The steep gravitational potential well compresses vertical motions and strengthens shear, both of which raise the threshold for large-scale fragmentation. Without a strong bar to drive shocks in flow, is slow and organized, and gas accumulates only in small quantities before either forming stars in compact knots or feeding the innermost accretion structures. The stellar velocity field echoes this order. Dispersions are high and nearly isotropic in the immediate bulge background, while the nuclear disk rides inside with low dispersions and high rotation. As a result, the nucleus retains a layered form hot stars in many orbits, for the background cool stars in a thin plane for the embedded disk, and wisps of gas and dust tracing the same plane. Despite this coherent picture, an unresolved mystery remains in the exact identity and prominence of any nuclear star cluster. In some galaxies, a distinct compact star cluster rises above the surrounding bulge light, carrying a well-defined half-light radius and a separate mass profile. In the Sombrero, the bright bulge and glare from the central light makes such a component difficult to isolate. Some analyses favour a modest nuclear cluster superposed on the thin nuclear disk. Others argue that the excess light is fully accounted for by the disk plus the smooth bulge profile. The distinction matters for formation pathways. A true bound nuclear cluster often records repeated inward migration and merging of dense star clusters, while a pure nuclear disk points more directly to in situ star formation from inward drifting gas. Present data allow both readings within uncertainties, and the answer likely involves a mixture in which a very compact cluster, if present, contributes less mass than the flattened component, but adds to the central concentration of light. The dynamics of dust at these radii highlight the delicate balance at work. Grains survive where column densities are high and radiation is filtered by prior layers, but they are eroded by sputtering in hot gas and by hard photons near exposed lines of sight to the nucleus. The narrowness of the observed filaments suggests that most dust resides in shielded streams close to the plane, where it can persist long enough to act as a tracer of orbit families. As those streams settle, they mark the pathway by which cold material crosses from the inner ring to the nucleus without being stirred into wide plumes. Over times longer than a galactic year, the filaments may fade, replaced by new ones that follow slightly different angles as the disk and bulge reshape the weak non-axis, symmetric pattern that guides them. Energy sources in the nucleus are layered rather than focused. The dominant field is old starlight from the bulge. The next contribution comes from the compact accretion source, faint but hard. The smallest share arises from scattered young stars formed in the nuclear disk. Each source heats dust differently and excites gas lines to different degrees. In the Sombrero, the balance favours warm, low ionization emission, with little blue continuum from hot stars, a mix that supports the view of a nucleus that is active at low levels but not starbursting. This arrangement preserves the clarity of stellar absorption features in the integrated spectrum and keeps the nuclear colours anchored in the red with only subtle deviations at ultraviolet wavelengths. Planetary scales in the nuclear region would feel the crowding in light more than in gravity. A planetary sky within the thin nuclear disk would blaze with the glow of the bulge on all sides, with red giants and horizontal branch stars thick on the eye, and with the dark dust threads carving narrow shadows against the glare. The interstellar medium would be thin, warm, and stratified, with low extinction between nearby stars compared with the ring, but with greater overall brightness from the background. The far infrared background from heated dust would be present but subdued relative to the ring. The near-infrared and optical glow would dominate. Occasional variable sources such as novae in old systems and the mild flicker of the central engine would add small rare transients to the light. On human timescales, the positions of dust filaments would remain fixed. On geological timescales, they would drift slowly as gas migrates inward. A lesser detail of technique links dynamics to mass. In the nuclear zone, stellar absorption lines broaden and skew under the combined influence of rapid rotation in the thin disk and high dispersion in the surrounding bulge. By fitting full-line profiles rather than just widths, observers extract higher-order moments that separate these components and reconstruct their relative contributions to mass and light. Applied to the Sombrero, this approach recovers a cold rotating contribution at the very centre, embedded in a hot background, exactly the configuration suggested by imaging. It also constrains the central mass concentration, indirectly tying the next step of analysis measurement of the central black hole to observed gradients in rotation and dispersion. Chemical clues in the nucleus extend the story of enrichment. The central stellar populations remain metal-rich and alpha-enhanced, in line with the bulge, while the minor young component in the nuclear disk carries metallicities near those of the inner disk gas from which it likely formed. Dust features in the mid-infrared, already modest in the inner disk, become fainter still as strong radiation fields and low gas densities erode small grains and molecules. The net effect is a nucleus that is chemically mature dust poor compared with the ring, and only lightly replenished by ongoing low-level star formation. Secular evolution continues to shape the nucleus quietly. Weak torques from any inner oval and tightly wound spirals exchange angular momentum between the nuclear disk and the surrounding stars, allowing gas to settle deeper, and stars born in the plane to diffuse slowly outward in radius. Star clusters that form in the inner ring and migrate inward through dynamical friction could in principle contribute to the nucleus over long spans. Whether this channel has been significant remains uncertain, because the observed nuclear excess is small and easily swallowed by the bulge's steep light. If it occurs, it would reinforce any compact nuclear cluster that might already exist, thickening it slightly, while leaving the thin disk intact. In summary, the nuclear region of the Sombrero is a calm, stratified core where an overwhelmingly old stellar population surrounds a very small, rapidly rotating stellar disk, intertwined with thin dust filaments and sparse ionized gas. The consensus elements are clear: a smooth, bright nucleus dominated by ancient stars, a thin nuclear disk aligned with the galaxy's plane, low turbulence and ordered rotation for gas, and a compact hard spectrum source that signals a faint active centre. The lesser-known texture includes evidence for a small younger stellar sprinkling in the nuclear disk, and the possibility still debated of a distinct nuclear star cluster that is hard to isolate against the bulge. The unresolved questions concern the relative roles of in situ star formation and inward cluster migration in building the innermost stellar excess, and the exact partition of mass among bulge, nuclear disk and any cluster. On the scale of worlds, the nucleus would be a sky of steady brilliance and fine shadows, a place where light is abundant, gas is thin, and change proceeds at the measured pace of stars orbiting deep within a quiet well. At the very centre of the Sombrero Galaxy, gravity gathers into a compact mass that rules the innermost orbits. The consensus view is that a supermassive black hole sits here, its presence inferred not from direct sight, but from the speeds with which nearby stars and gas move. Within a tiny radius, the line of sight velocities climb to values that require a deep potential, well, much steeper than the surrounding bulge can provide. Models that fit these motions favour a central mass of roughly 1 billion times the mass of the Sun large. For a galaxy whose stellar disk is modest and in keeping with the prominence of its classical bulge, this black hole does not appear as a bright quasar, it smoulders. The nucleus is active at a low level, emitting faint hard radiation and a compact whisper of radio light, the marks of a central engine running on a thin diet. The evidence arrives along several lines. High-resolution spectra of stars in the immediate core show absorption features broadened by rapid random motion. The increase in velocity dispersion toward the centre is sharper than expected from the stellar mass profile alone. Gas offers a complementary trace. Where a thin inner disk crosses in front of the nucleus, emission lines narrow and tilt in a way that betrays fast rotation in the central few tens of parsecs. Fitting these velocities with orbit families that include a point-like mass produces a consistent answer, an object far more massive than any cluster of stars can remain, without quickly collapsing, and far more concentrated than any ordinary stellar distribution. The simplest interpretation is a supermassive black hole anchored at the dynamical centre. Despite the small fueling rate the black hole announces itself across the spectrum, in X-ray images the nucleus appears as a compact hard source atop a fainter diffuse glow from hot gas in the inner halo. In radio maps, a tiny core stands out with a flat spectrum, and on the smallest resolved scales some studies hint at a stub of collimated structure, a suggestion of a very short jet that never grows into a large bright plume. In the infrared and optical bands, the glare of old stars dominates, yet delicate emission lines of low ionization species mark a warm, rare medium close to the centre. Taken together, this signature resembles that of many nearby bulge-dominated galaxies in a quiet phase, a central engine present and awake but far from its maximal output. A lesser-known detail concerns the temperature and density of gas available to feed the whole. The inner halo holds hot plasma at millions of degrees Celsius that drifts slowly toward the centre under gravity. In simple estimates, this gas could supply a much higher accretion rate than is observed. The mismatch suggests that most of the infalling material never reaches the event horizon. Instead, it likely joins a radiatively inefficient flow in which much of the gravitational energy does not become light but remains as heat carried inward or outward, or is lost to a weak wind that carries mass away before it can fall deep. In such flows, the X-ray luminosity rises only gently with the feeding rate and the spectrum stays hard. Sombrero's nucleus fits this quiet pattern. The surrounding stars also play a role. Winds from old giants and dying stars continuously return gas to the central few hundred parsecs. In many galaxies, this local supply is enough to brighten the nucleus episodically. In the Sombrero, the strong vertical gravity and the modest level of turbulence hold most of this material in a thin rotating layer, aligned with the plane where it can be heated, ionized or gently converted into stars before it reaches the last stable orbits. The faint young stellar sprinkle identified in the nuclear disk is one sign of this competition for fuel. Another sign is the weakness of broad emission lines that would betray very fast gas near the hole. Their absence means little cool gas survives close to the centre, or else that the viewing geometry hides the region where such lines would originate. The black hole's mass sits comfortably on the widely discussed relation between central mass and bulge velocity dispersion. The Sombrero's bulge is large and dynamically hot, and the estimated central mass follows the trend that more massive higher dispersion bulges host heavier black holes. This concordance does not prove a single growth path, but it aligns with a picture in which the bulge and the black hole grew in step early, perhaps during a brief period of rapid inflow when the universe was denser and gas accretion was efficient. The present nucleus running quietly at a tiny fraction of its maximal power would then be the long afterglow of that formative time. An unresolved mystery concerns the spin and feeding history of the central black hole. Spin affects how efficiently accreted mass turns into light and how readily a nucleus can launch even a small jet. Direct measures of spin remain uncertain here. The faintness of the nucleus limits the diagnostic lines and continue that models use to infer rotation. Likewise, the duty cycle of activity remains unknown. Did the Sombrero's nucleus pass through brighter phases long ago, perhaps when minor mergers or internal instabilities sent more gas inward? Or has it always lived at low ebb after its early growth? The halo's faint stellar streams show that small companions were absorbed over time, but whether those events reached the centre with enough coal gas to light a strong episode is an open question. The nucleus keeps its past largely to itself, and present evidence allows several histories that converge on the same quiet outcome. Closest to the event horizon, the flow geometry also remains a subject of study. Radiatively inefficient accretion can take several forms. A hot, thick flow that swallows some mass and drives some away. A two-phase mixture where cold clumps orbit within a warm medium. Or a series of layers in which angular momentum moves outward through tangled magnetic fields. Each variant leaves subtle fingerprints in the spectrum and variability. The Sombrero's nucleus varies only weakly and shows a hard spectrum without strong thermal peaks supporting a hot, thick flow view, but the data are not exclusive. Finer timing studies and deeper X-ray spectra could narrow the possibilities, yet the low luminosity sets a limit on what can be teased out. The black hole does not stand alone. It sits within the steep cusp of the bulge's light and near the tiny nuclear disk. The alignment of their axes indicates that the central mass shares the global orientation of the galaxy. If the whole spins rapidly, its axis might align with the inner disk, over many precession times through the gentle torque of accreted gas. Any small jet would then tend to point close to the disk normal, as suggested by hints in radio maps where the faint extended emission is nearly perpendicular to the plane. The brevity of the feature, if real, fits the low power of the engine and the density of the central starlight, which can confine and damp a weak outflow. On planetary scales, inside the nucleus's sphere of influence, the presence of the black hole would be felt not as a dramatic beacon, but as a slight enhancement of the gravitational field against a very bright backdrop. A world orbiting a star in the nuclear disk would see the sky dense with the bulge's old suns, and almost featureless in gas emission. The central source would add a pinprick hard glow, detectable to instruments but barely changing the night. High-energy particles from the faint nucleus would arrive as a small background atop the broader cosmic ray field, and their influence on atmospheres would be minute compared with the radiation from nearby stars. The dominant effect would remain the steady gravity that sets the paths of stars through the innermost few parsecs, tightening orbits by a small but decisive amount and sharpening the shear across the nuclear disk. A lesser detail of the method links the black hole measurement to the shape of the stellar velocity ellipsoid. When observers model the central dynamics, they must allow for the fact that stars do not move isotropically. In the Sombrero fits that include mild anisotropy in the bulge, reproduce the line profiles with the central point mass better than isotropic models do. This nuance matters because anisotropy can mimic or mask the presence of a compact mass if not treated carefully. The agreement between gas rotation curves, stellar dispersion profiles, and the shape of absorption line wings strengthens the conclusion that a real concentrated mass is present and fixes its scale within reasonable bounds. The black hole also participates in the slow energy economy of the galaxy. Even at low output, the nucleus heats a tiny volume of gas, and through occasional outbursts it may